Good morning, everyone. If anyone wants to test out their camera or mic or slides before we get started, now's a great time. Got about 9 minutes before the session starts.
Hi, can you hear me?
Yes, I can. Good morning.
Good morning, thank you.
Hi, Jeff. Yes, I am. I'll be helping with all the tech stuff. Mostly just making the current presenter and the one on deck co-host so they can share their slides. But if anyone has any technical questions, I'm happy to help. And yeah. Is it possible to get the chairs on video and mic? Okay, so Liam just joined. Liam, I think you're our first presenter. Do you want to take a moment and test your slides out?
Yeah, perfect. You can hear me okay?
Yes, loud and clear.
Okay, great. I will just do that now. 1 second.
Okay, should now have permission to do that.
Perfect.
And anyone else who's on the call who would like to do this as well, let me know and I'll nominate you and you can test your slides out.
How are we looking here?
Yeah, that looks great.
That's good?
Yes.
Okay, great. Thank you.
No worries. Thank you. I'll just keep you as a co-host. And Jeff and Lee are illustrious co-chairs. Are you able to jump on?
Yeah. Jeff is recommending that I use those timer background things, so I'm checking it out.
Okay, great. Yeah, I think the second you switch to it as your background, the timer will start.
So I've never played with backgrounds before. Let's see.
Yeah, I've got a timer on my phone going as well. If you don't figure it out, it's okay.
Yeah, that was what I was planning to do.
Yeah.
Yeah, it's completely up to you. Yeah, you can forego it if it's too much trouble. Oh, and
if it doesn't work out, Lisa, I can try and do all the timing.
Okay. Like, how do you even switch a background?
As you can see, I've got to change that.
Yeah, so Lee, if you go to your stop video button, the little pop-up menu on the upper right of that button, there's a choose virtual background option. You see that?
No.
If you just put
Is
your,
app or just for this meeting?
So I don't understand the question. Can you repeat that?
I don't know how to better explain myself.
So it's within Zoom. Within Zoom, if you go to your video options, where you can select your camera, there's a menu option that says choose virtual background.
Aha. Thank you.
Yeah, and then you hit the little plus thing that says add image or video, and then you can add the video of that background. Yeah, Jeff's got it.
Interesting. So did Jeff get out of the way?
So you just block your screen, which I have a little slider on my camera that allows me to block the screen.
Oh, see, that's why I didn't want to do this. It's so awkward because I'm like,
I think the main thing is the color will tell you. You know, I think yellow starts at like 4 minutes or something, and then red is the Q&A. So.
but anyway, I think we should only have one person timing.
Yeah, and what I thought would be whoever introduces the speaker, the other person can start the timer, except for when you introduce me for my talk, you'll have to try and do both. And if you give me a little extra time, that's fine.
I feel really awkward being in front of this.
You don't have a block
No,
for your
I
camera?
Maybe I can like.
The other thing you can do is cover your camera with like a little piece of tape, or and then just take it on and off as you want to appear and disappear.
I'll look for like a business card. Really. That works. Oh,
That
cool.
looks good.
Got about a minute before we get started. I'm just going to go ahead and hit the record button. You're going to hear a lovely prompt from Zoom.
Recording in progress.
I'll let you guys take it away whenever you're ready. You got a couple seconds left. So.
Yeah, why don't we start with some introductions, and by the time we're done with that, we'll be right on time. So I am one of your chairs or hosts today for the session Space Weathering and Regolith Evolution, which is parallel session 2. My name is Jeffrey Gillis Davis, and I'm at Washington University in St. Louis.
My name is Alicia. I work out of Impact in Colorado, and I'm a hopefully final year grad student, and I study lunar dust and plasma dynamics. So welcome to our session. Today we have 6 10-minute talks and 4 lightning talks, and then we'll have a 45-minute discussion. Is there anything you want to add, Jeff?
Nope, I think that is it. Oh, there's just the general timer. Probably everyone's used to it, but it'll be for the 10-minute talks, you get 6 minutes of green, and then at 4 minutes left, it turns orange, and you should be hopefully wrapping up. And then there's the final 2 minutes where the clock is red, and that's your question and answer time. So if you eat into that, you eat into your question time for the 10-minute speakers. And then for 2 minutes, we use a 2-minute timer for the lightning talks at the end of the session. So with that, we have our first talk is Simulating the Diffusion of Protons in Amorphous Silicates by Liam Morrissey. Take it away, Liam.
Sure. Sure, I'll just share my screen. If you can just let me know if you're able to see that working, that'd be great. You're able to see that?
Yep, looks good.
Okay, great. Well, then I'll get started now. All right, so hi everyone. My name is Liam Morsi, and as was just introduced, I'll give a talk today on simulating the diffusion of protons in amorphous silicates. So what we're going to do here is I'm going to begin with a background. So basically, the sun emits a stream of charged particles known as the solar wind, and this solar wind is comprised 95% of H plus and 5% He double plus. Now, unlike Earth, the lunar surface is constantly bombarded with this solar wind with very limited protection. Furthermore, recent OH discoveries on the moon have suggested that solar wind H implantation and its subsequent diffusion is a key precursor to both OH and water products. However, we do need a better understanding of H retention and H diffusion mechanisms in order to improve these water production models. Now, common statistical-based models, and these are the models that you'll often see used, what they do is they assume various activation energies and diffusion coefficients. Now, in contrast, we can use molecular dynamics, or MD, to actually investigate the diffusion on the atomistic scale. The benefit of this is that when we run these, we're actually simulating the process on the scale in which it's happening. Now, previous MD works on H diffusion in amorphous silica have had a large discrepancy in the previously predicted H diffusion coefficients. So you can see in the table on the bottom, we have a range of orders of magnitude of about 5. And this is a problem because if we want to rationalize that we can use MD, we're going to need to rationalize why we're seeing such a large range in predicted values for simulations that look very similar. So basically what our purpose was that we wanted to investigate the source of these discrepancies in previous MD studies. And then after doing that, we wanted to use MD to better explain the mechanisms of H diffusion in amorphous silica across a wider range of temperatures, which may be relevant for lunar surfaces. Now, briefly, what our methodology was that we used MD to simulate the movement and interactions of all atoms in the system by taking a periodic amorphous silica slab and preparing it to the desired temperature using a reactive interatomic potential. Now, we decided to use an amorphous structure because we wanted to mimic the weathered glassy silicates commonly found on the moon. After we developed our amorphous structure, we then added the H atoms and we tracked the individual movement of each atom for 10 times longer than previous studies. And that worked out to about 4,000 picoseconds. And I've bolded that B because I'm going to talk about that later, but I want to just kind of flag it for you. Now I'm going to move into our results. So first, you can see on the right, we have a standard Arrhenius plot, which we can use to track the diffusion coefficients and the activation energies. Now, we actually observed 2 activation energy regions, one in the low temperature region between 100 and 450 K, and one was a higher temperature region. Now, previous similar studies on H diffusion in silicates have also observed these regions. But what's interesting is that this study said that the movement or the diffusion in that low temperature region was actually not diffusion, but only lattice vibrations found at low temperatures. The problem is that while these studies made this finding, they didn't actually investigate the mechanism of the diffusion, and were unable to answer the question of, are we just seeing limited motion or are we seeing no motion at all? So basically, we wanted to actually better explain what was going on here by tracking the individual motion of each H atom as a function of time. So when we do this, we can get a better sense of what's going on with the individual movement of each proton within that silicate. So as opposed to the constant motion that you'd expect to see in a diffusion system, we actually noticed that the H atoms instead underwent intermittent jumps from one O to another across the SI-SI midplane. We also noted that the number of these jumps increased with temperature, and we found an average jump size of about 3.4 angstroms. Now, the concept of solar wind implanted H diffusion by jumps was actually first posited in 2006 by Sterakina et al. But the problem is because these studies weren't actually simulating the diffusion on the scale in which it was happening, it was only a theory that wasn't actually being shown. So there's still a lack of agreement over whether that was the actual mechanism of diffusion. After showing that motion, we then wanted to find a way to better track diffusion beyond just the MSD. So we actually took these motions and we compiled them into what we call a normalized jump rate, where we actually take the total number of H jumps and we divide it by the number of atoms multiplied by the duration of the simulation. And you can see those findings in the figure on the right. What's important to note is that we did observe a jumping mechanism across all the temperatures studied between 100 to 1500 K. Furthermore, and perhaps even more importantly, we did find jumps in those low temperature regions. Because we're actually seeing jumps from one O to another, this means that diffusion is present at these low temperatures. Now, as we move up to higher temperatures, we obviously see a significantly higher jump rate, which means that the activation energies are significantly less influenced by the lattice vibrations. Basically, what these findings highlight is the importance of considering the individual atomic motion and not just the net MSD at the end of the simulation. Finally, we actually wanted to compare these findings to experimental methods and other similar models. So you can see in the figure on the right, we have a compilation of various MD studies and experimental works as adapted from Fink et al. The various experiments are found in the small circles. Our MD work is the large black circle, and the other MD works are found in the larger squares. You can see that our simulated diffusion coefficient at 300 K compared very well with experimental H in vitreous silica. And we note that H in vitreous silica probably best represents our system. Furthermore, our results are much more accurate than found in the previous studies. But one thing that we did find interesting in this is that if you look at the bottom of this plot in the light green, you can see that H in irradiated oxide had a far, far lower diffusion rate. And it's important to note that our MD model was actually done on a defect-free lattice. So this kind of flagged to us to want to know what's actually going on here, because we know that H diffusion in irradiated oxide is lower, and we know that if that irradiation forms defects, so we kind of wanted to see whether this was traps. So at the end here, we actually ran some MD simulations to verify H trapping out voids, where we actually took hydrogen atoms in yellow and we placed them at the edge of a void in purple within an amorphous silica at a higher temperature. What we actually found was that the atoms always stayed tracked to the defect, meaning that we actually demonstrated that that diffusion within a defect will be much lower, and that defects created by solar wind weathering would likely further reduce H diffusion in regolith. So I can basically clue up here with a couple of the implications of our findings. First, from an MD point of view, we actually showed that H diffusion in silicates occurs via random H jumps, and this is very different than a constant motion mechanism. So therefore, at low temperatures, these jumps are rare, and we need to simulate for longer. Longer simulations allow for better statistical sampling of jumps and the atomic movement. And as we noted, we simulate 5 to 10 times longer than previous similar studies. We think that because we're simulating for longer and sampling better, we're actually getting a better accuracy. And finally, there's also implications from a lunar point of view. We know that lunar surfaces have a large range of possible temperatures, depending both on the location and the time of day. What this study demonstrates is that H diffusion via jumps does occur at these low temperatures. And because of this slow diffusion combined with traps at vacancies, this means that implanted hydrogen atoms are likely outgassed slowly and can saturate the regolith surface. Furthermore, we know that the solar wind is also comprised of higher mass ions that have a larger energy during impacts. These impacts may potentially be leading to temporary high temperature spikes within the regolith that may also be further driving diffusion. And this is kind of our ending concept teaser that we actually want to look at in a further future study. Thank you for listening. And does anyone have any questions?
Yeah, if there are any questions for our speaker, we have a little bit of time.
Yeah, and this is Tom Orlando. That was a really nice talk.
Thank you.
One thing that would be good to point out is the H atom diffusion. When it gets to the surface and it traps, or it could interact with an oxygen and lead to the formation of an OH. So, and in fact, this is also the mechanism for what people are referring to as OH diffusion.
Definitely, yeah.
Okay, so it's an important point. And these are really important simulations because you're really getting to the bottom of it. I guess the question I have is, the lunar regolith has a lot of other stuff in it. So, what's your next step?
So I think you've definitely gotten to the crux of kind of what we're doing. And with any simulation, especially in MD, you kind of want to start with the best thing you can represent, and then you want to layer in complicating factors so we can continue to get more and more realistic. So basically, I assumed it's an amorphous silicate, but we know that within that amorphous silicate, first off, there are going to be other elements because it's likely more like a feldspar or an albite or a northite. So we can change the potential type such that we're simulating a structure that's more similar. And then what I also want to do is I want to layer in defects and boundaries and vacancies such that I can say that this is a weathered silicate and this is a non-weathered silicate. And I can actually understand what's actually going on with the diffusion. I don't think the mechanism will change, but I do wonder if the rates will change with the proportion of defects, as an example.
Okay, thank you, Liam.
Yep.
That sounds great. Okay, so we're going to move along to our next speaker. I asked people if you still have questions for Liam or anyone else, put it in the chat. Start your text with a Q and square brackets, and even put the speaker's name.
Yeah, and I'll also share my email in the chat if anyone wants to follow up with me after. Thank you. Yeah.
Great. So our next talk in the session is atomic scale simulation of lunar water retention induced by space weathering. The authors are Huang, Nomura, and Wang, and the speaker is Zhu Huang. Can you share your screen?
All right, can anybody see my screen?
It looks good. Looks a little small, but I think it's all right.
Let me retry it. Let me reshare it again. How about now?
I think that'll do it. It looks like it's full screen.
Okay.
It's not presentation.
Okay, thanks. All right. Good morning or good afternoon. I'm Ziyu Huang from University of Southern California, and I work with Professor Joseph Wang. This work is also collaborated with Professor Kenichi Nomura and Professor Aicho Nakano. This talk is about atomic scale simulation of lunar water retention induced by space weathering, and I will introduce some updates on implementing molecular dynamic simulation to planetary science problem. Well, there are many space weathering processes like solar implantation, micrometeor impact, or dielectric charging, which can lead to dielectric breakdown. We want to start from a problem that is strongly related to those processes, which is the lunar water cycle. And there are multiple sources for lunar water, and in this talk, it's focused on solar-related sources. Solar implantation provides hydrogen to the lunar surface, but since the temperature is not high enough for water formation, it requires additional energy. Well, micrometeor impact and dielectric breakdown could possibly provide enough energy, but it could also provide too much energy that can make the surface lose water. So in this way, we use atomic scale simulation to see if we can evaluate the contribution of those of each process. The model we use is reactive force field coupled with molecular dynamic simulation, and also a polarizable charge equilibration model. The advantages of this potential are, for instance, it can directly simulate chemical reactions by bond forming and also bond breaking. And it can also capture the atomic structure of the regulus, like crystal structure or amorphous porous structure. So first, we introduce solar implantation and sputtering. We'll limit the case to PSR since there's no photo disruption and the temperature is low, so that the thermal disruption is low as well. The horizontal velocity is drifting velocity of solar wind, which is about 400 kilometers per second. And the vertical velocity is calculated by the plasma sheath theory, which is the ion crystal velocity square root of electron temperature over the mass of protons. And the value is about like 40 kilometers per second. And after each implantation, we relate the surface to the original temperature, which is about 100 Kelvin. Making sure there's no energy residue before the next implantation cycle. The blue particles are hydrogen, and we continue to implant more hydrogen items. So as number grows, we can see like more and more particles are reflected. Well, this reflection of solar wind is consistent with observation by Kaguya and also Chandrayaan-1, but it's not a focus today. And after we implanted about like 3,000 hydrogen atoms, we can see the surface is almost covered by hydrogen atoms. And there are even some water molecules that are sputtered from the surface being injected. And then we use group analysis to identify each molecules and chemical groups. And the left two figures are the number of hydroxyl group, hydrogen molecules, and also water molecules. The upper one is above the surface, and the other one is on beneath the surface. Well, the data shows that most of the hydrogen atoms from solar wind are turning to hydroxyl groups and also hydrogen molecules, H2. Water molecules are also detected, but there are very few of them. When we convert it to a 60 micrometer dust, the OH and H2O abundance is less than 1 ppm. But it shows that incoming solar wind hydrogen atoms can combine with hydroxyl and then form water molecules, although it's very unstable and easily to be sputtered. Another interesting thing we found is that although the hydrogen molecules H2 number is still growing, the number of hydroxyl and also water molecules are becoming stable. So this indicates that the surface will be saturated with hydroxyl and water molecules if the implantation continues to go on. And the saturation time we found is about 400 days based on the solar wind conditions and local temperature. And then we move on to micrometer impact. We keep the implanted samples from previous simulation and then replicate it in X and Y direction by 4 and 4. Then we place another phase silica sphere on the top and then assign impact velocity to it. The snapshot showing the bottom, we created the surface by alpha shape method, and we can see the mini crater formation as well as some molecules and atoms being ejected from the surface. We tested 4 different velocities ranging from 8 km per second to 20 km per second. The velocities are all perpendicular to the surface, and we will definitely include the effect of impact angle in the future. The left figure is the total water molecules, and on the top right is the number of water molecules above the surface, and the bottom right is for those on or beneath the surface. And we found that in total, micrometer impact always produce more water by providing energy to hydroxyl group for recombinated desorption. But at the same time, if you look at figure C over here, the retention of water molecules at impact site is strongly related to the velocity. So for 8 km per second, if you can see, the abundance of water molecules almost go back to the original abundance. But for 20 km per second, the impact almost double the water abundance. And for those above the surface, they're being classified as molecules ejected from the surface. And almost 50% of them escape from the moon, and 50% of them contribute to the exosphere, or they are redistributed to the ground. And when we look at the impact side, we found that the post-impact side is becoming amorphous and also porous. The figure on the right shows the silicon oxygen 4 tetrahedra, and it shows a significant change of the surface atomic structure. The impact removed the hydrogen on the surface, making the surface fresh again, and this could be ready for another implantation cycle. And also the amorphous structure make it possible to deposit more hydrogen atoms in the implantation, and thus more water molecules could be formed when the second impact occurs in this post-impact site. Regarding dielectric breakdown, for the interest of time, I will refer the formation of water molecule to the last ESF talk. This is a QR code, and also a recent GR paper we published. What we want to update this year is that the electric field can also trigger desorption, which is a loss mechanism. And compared to dielectric breakdown, the desorption starts at a lower electric field level. This can be seen on the right. When applied an electric field about like 10 to the order of 5 voltage per meter, the number of molecules in total stayed relatively stable, meaning that the electric field won't break H2 or H2O. But the hydrogen molecules and also water molecules are leaving the surface. That can be seen from the lower 2 figures. And in contrast to thermal desorption, this occurs more frequently in colder region. And originally we thought that like cold region, especially PSRs, are very quiet and everything stay as it is. but the deep dielectric charging theory shows that there could be some loss mechanism just because the surface is too cold. And here we put a table as a summary listing each space weathering process and the mechanism of water formation and loss, and also the area effect. The implantation and micrometer are almost everywhere, but there's different conditions, like the solving velocity and implantation angle. Well, dielectric breakdown occurs mostly in colder regions. And currently, we can conclude that within PSRs, the combination of implantation and micrometer impact can continuously accumulate water molecules and garden them into a deeper depth. And there are some periodic feature of the combination to the contribution of water molecules. And future work will definitely include the total contribution of those space weathering effect and also model the global lunar water distribution based on the atomic scale simulation. All right, with that, I will take any question you may have. Thank you.
Sorry, I've got a timer going, but we have a quick 1 minute for anyone who has a quick question for Zhu.
There's a question in the chat by Parvati. She says, excellent talk. This is really interesting and important work. Have you tried any direct comparisons of simulation results to experimental results? The simulation seem mature enough that you could potentially do that, which is great.
Oh, thanks for the question. Yeah, we're trying to implement the experiment of dielectric breakdown in our lab, and also we're trying to find some experiment data for the micrometer to be compared to the MD simulation. And this is definitely our future work, but currently I don't have any updates for that.
Great. So, if you're okay, can you continue to respond to the rest of the questions in the chat?
Okay,
and we
thanks.
can move on to our next speaker, who is also our co-chair, Dr. Jeffrey Gillis-Davis, and his title is Analyzing Dual Laser Space Weathering Effects.
Okay, I'm trying to share. Mike, it still says host disabled participant sharing screen for me.
Interesting. Are you sharing? Sorry, that's my bad. Do you have a second account on that I can? Oh, that's probably why. Okay.
Yeah.
Okay, try now.
Okay. All right, so a little shift in things. We're going to move on from ions to micrometeorite bombardment of space weathering. And this is work that I'm doing as part of our SSERVI ICE5O with collaborations from University of Hawaii and San Francisco State. So I'm going to talk about, I'm actually just using long pulse laser space weathering method to make agglutinates. All right, so in the sense of lunar space weathering, we have a number of different parameters to try and recreate with laser space weathering, and I've outlined 5 of them here. The first is rims that occur on minerals, and those rims, in this case an inclusion-rich rim, often have nanophase iron in them. And with short pulse lasers, we can recreate that feature. Another very common feature in lunar regolith are the agglutinates, which in a mature lunar regolith can comprise up to about 60% modally of the regolith. And with the short pulse only laser, we cannot produce these agglutinates. And by the lack of producing these agglutinates, we also don't make a lot of nanophase iron and the microphase iron. And this feeds into the magnetic signature that was measured by Morris in his 76, 78, and 80s paper, where it became a maturity index where the I sub S normalized to the FEO matches and is used for maturity parameters. But in measuring isobesive FEO of our short pulse laser space weathered regolith, we don't get very high in isobesive or FEO. We only get about 10 or 14, which is very immature. So we don't replicate that feature very well. In the case of spectra, we do that pretty well. Here on the plot in the lower left, you'll see there's 3 spectra. One is of a rock, the dotted line. And you can see that for a lunar, in this case a Mare rock, we have a very good absorption band at 1 and 2 microns showing pyroxene. But as we look at a soil that has been naturally space weathered on the surface of the moon, but is of similar composition, the black line there, you can see that those mafic absorption bands have now just essentially almost disappeared. The spectrum is darker, it's lower down. And if we normalize that spectrum at 500 nanometers at 0.5 microns, which is the line with the dots, you can see that the spectrum is also redder than the typical fresh rock material. In other words, it increases in reflectance as it increases in wavelength, and these are all key features in lunar space weathering. And the short pulse laser reproduces some of the darkening, definitely the redding, and a little bit of the loss of the spectral absorption, but doesn't completely or nearly erase them like we see on the moon. And then on the lower right, there's XRD analysis by paper by Taylor et al. In 2019, which minerals show good peaks that are related to elements and elements in different mineral lattices. And for lunar regolith, where there is a lot of agglutinates, there's this amorphous hump that you can see on the very low part. It doesn't have Bragg scattering because it's just elements in a glass. So it's another criteria which we need to be able to recreate with laser space weathering, but we don't. So our motivation was to add a second laser. So typical lunar space weathering, we use the short pulse, as I mentioned before, which is a 10 nanosecond pulse length. That's about 30 millijoules per pulse. And this creates a lot of vapor and makes rims on materials. But what we've added is a longer pulse, 100 nanosecond pulse, higher energy at 300 millijoules per pulse. This creates more of the melt deposits and makes agglutinates. So on the image below that, you'll see there's 2 lasers. The blue one is the short pulse. It goes through a beam splitter and then into the chamber. The other laser, it bounces off and gets combined with that pulse. So we're hitting the sample at the same time. The laser energy then is directed or redirected in the top images down into a vacuum chamber. So our experiments are done under vacuum. And we also use loose powders to more faithfully replicate a lunar surface. And that actuated mirror actually steers the beam in X and Y. And the lunar plasma actually gardens the sample. With each shot, it creates little craters. And in the future, those open circles, we're going to be adding temperature controls as well as the addition of volatile species. So as I mentioned before, the spectra that we see, so on the left is spectra of San Carlos olivine that we have laser weathered with the short pulse spectra. You can see very top, you have a nice 1 micron absorption, and then after about 40 minutes, it becomes what we call spectrally mature. It doesn't change much, even if we add more laser radiation. You can see the spectrum is red. The 1 micron feature is still somewhat present, and it has darkened. On the right is our long pulse spectra. Again, this is San Carlos olivine. And as you can see, as we move, in lower albedo, our longer duration of long pulse, at 32 minutes, we have made a spectrally mature material that the 1 micron band is, essentially erased. It is definitely flatter, or what you may call bluer, than the short pulse laser weather measurements, and it is definitely a lot darker and more closely matches lunar materials that have been space weathered. And just for a comparison, I just popped up there on the green line. The short pulse lasers, you can kind of compare, where we are at the maximum amount of laser space weathering with short pulse versus the maximum kind of intermediate amount for long pulse weathering. We can take these spectra, and this is work that Heather Kaluna has done for this project where we do principal component analysis, and we wanted to compare this to real Apollo samples to see how we're faithfully reproducing our weathering. So on the right, on the bottom we have PC1, which corresponds mostly to albedo, and PC2 on the y-axis, which mostly correlates with the continuum slope. We have Mare Highlands and Apollo 14 samples with the different color codes. The size of the samples correlates with maturity. These are samples that have been taken from the LSCC, and we have the I sub S over FEO. So we're able to correlate spectral parameters here with I sub S over FEO, or maturity. And you can see that they dominantly move from immature to mature. They get darker and they get redder. Now I've popped up these green circles, are results from our short pulse only laser. One takeaway is the immature material from the moon is still, more mature than what we did with the short pulse laser in this scenario. But you can see the trend is roughly what we see, but definitely steeper. We get it a lot more red with our short pulse. Now we'll pop up the long pulse laser. So these circles, the yellow-green circles, are the long pulse laser results. You can see that we are now able and capable to get into the same field in the PC space for PC1 and PC2 compared to fresh and mature lunar materials, but particularly Mare materials. And this again is also showing with PC3 and PC1, where PC3 here is spectral contrast, so loss of spectral feature. Again, we're seeing that we match Mare material very well. Next are some SEM images that I'll go over really quick. Left is a lunar agglutinate. Right are some laser agglutinates that we've made. They look pretty similar. The far right image just kind of shows we can make them of all different sizes. Vesicularity is also a feature that we need to replicate. We do see we create some vesicles. Left is Apollo. The two right images show some vesicles, as well as the microphase and nanophase iron, kind of zoomed in. Then this is a cross section of the agglutinates as well, showing, again, different kind of nanophase iron, different structures, complex and simple balls, and the nanophase iron. And then for our conclusions, with the dual laser experiments and only using San Carlos olivine, we are pretty well reproducing things. We're able to form agglutinates, and the big takeaway is that once we create these under vacuum, we can do other experiments, and we're still waiting to get some TEM and I sub S over FEO values for these materials. Thank you.
Yeah, thank you. Unfortunately, we're so out of time for questions. So let's just move on to the next speaker, and we can work on this in the discussion later. Our next speaker is Brittany Symes, and her title is Variation in Nanophase Metallic Iron Particle Occurrence in Exolved Space Weather Lunar Pyroxene. A lot of words I don't know.
Thank you, Lysia. Can you see my screen and hear me just fine? Yeah. Okay, great. Hi, everyone. Today I'll be sharing some of our recent work involving nanophase iron particles in a space-weathered lunar pyroxene grain. So nanophase iron particles are a frequently encountered product of space weathering, as Jeff mentioned, on lunar material, and I study these particles and other space weathering phenomena using transmission electron microscopy, or TEM. To give you an idea of what nanophase iron particles look like in the TEM, to the right here is a dark field image of an olivine grain acquired on our STEM instrument. And at the edge of this grain, you can see a space weathered rim. And upon close inspection of this rim, you can see it's full of nanophase iron particles. So these particles have been found in the space weathered rims of both iron bearing and also non-iron bearing phases due to a combination of effects that elicit their development both in situ and ex situ. That's a separate talk. Today, I want to talk about the iron bearing phases specifically. And recently, I've been reading about how olivine has been found to be more favorable for nanophase iron particle formation than pyroxene in laboratory experiments. And I'm curious if this is a chemically or structurally driven phenomena, or both. And is there a way to answer this question using returned samples? The primary limitation of natural samples being, of course, the inability to control the variable of exposure conditions. We simply don't know if two lunar regolith grains of different compositions received the same space weathering input, unless, of course, they're in the same grain, such as in prior work from our lab on chromite, ilmenite, and glass. But then you lose the structure component. So can we analyze two chemically distinct minerals, always guaranteed to be in the same place for the same amount of time, in the same orientation with virtually identical crystal structures? And the answer is yes. We can analyze pyroxenes, which are a very important rock-forming mineral on the moon, and they have a rather special cooling feature that we can use to address this question. Due to symmetry differences, which result in calcium incorporation, there's limited solid solution between the calcium-rich clinopyroxenes and the calcium-poor orthopyroxenes. And what occasionally happens during the cooling process is something known as exsolution. Using this phase diagram between orthopyroxene and clinopyroxene as an example, you can see that when a stable pigeonite solid solution cools, it reaches a univariate curve, and then the melt separates into two more stable coexisting pigeonite and augite phases. And this results in something that looks a little like this cross-polarized light image here. So there's our two phases. And as you can see in the center of this diagram, the augite lamellae form parallel to the 001 plane. So these chemically distinct domains are not random. They share symmetry components. So now we've got our second component of controlling our crystal structure. So we looked at one of these very interesting grains. We prepared a pyroxene from sample 71501 for analysis in the TEM using our FIBS SEM. You can see our final sample here in the secondary electron image. This pyroxene sample actually has two pyroxenes. The main target here labeled 1 pix, and adhered to the surface is our exolved grain labeled 2 pix. We used energy filtered TEM to visualize the exsolution lamellae. FTEM is a parallel illumination technique in which only those electrons that have lost a characteristic amount of energy are used to generate the final image. So when we center an energy selecting slit on a characteristic calcium excitation feature, this yields this image you see here. The more calcium rich phases are brighter. And then performing electron diffraction then allowed us to identify these two phases as pigeonite and 001 lamellae of augite. And you can see here next door is the unexolved pyroxene grain, which was also an augite. Moving the sample then to our STEM instrument, so now we're imaging with a focused probe. We acquired high-angle annular dark field, or HADF images. HADF is a Z-contrast imaging technique that helps us better examine the space-weathered rim, because here the more iron-rich phases are going to show up brighter. So now we're going to flip our contrast from the previous image. And upon close inspection of the space-weathered rim of the exolved grain, you can see that fewer nanophase iron particles form in the augite lamellae than in the pigeonite lamellae. In addition, we see nanophase iron particles forming up to 175 nanometers deep into the grain interior of the pigeonite lamellae. We don't seem to see this trend in the adjacent unexolved augite. It develops nanophase iron particles on the same order as the pigeonite lamellae, and we thought, maybe it's a difference in the iron content that could be behind this textural difference we see in the exolved grain. Okay, so let's take a look now at the composition. We next use the STEM's EDS detector to collect X-rays from these regions, from which we can reconstruct elemental maps. You can see here very nicely domains of augite and pigeonite based on segregation of the metal cations, magnesium, calcium, and iron. We also collected on the adjacent unexolved augite crystal. We can also quantify these data, which yielded these nominal compositions plotted here in this ternary diagram. And you can see, indeed, the pigeonite lamellae have more iron than the augite. So was iron the answer, was more iron the answer to our nanoparticle mystery? To make sure, we then turned to electron energy loss spectroscopy, or EELS, and we discovered it was probably not more iron, but different iron. EELS tells us not just chemical information, but can tell us about the oxidation state of the elements. And in the STEM coordination, we can acquire what are known as spectrum images, where an entire EELS spectrum is acquired at each pixel in a given area, and this generates a three-dimensional data set. Taking a look at a slice of this data corresponding to the characteristic iron excitation edges, we noticed dramatic shifts in the shape and onset of the iron L edge, which correspond to different oxidation states of iron. We found iron 2 in the pigeonite lamellae, iron 3 in the augite lamellae, and metallic iron in the nanophase iron particles. And using concurrent standards for iron, we can actually generate maps of multiple oxidation states from these spectrum images to have a better spatial idea of what's going on. And it's very clear here on the left that the pigeonite lamellae host dominantly iron 2 and the augite host dominantly iron 3. And when we map all the iron together with oxygen here in the center, you can see that the iron nanoparticles are indeed reduced as they anti-correlate with oxygen. So we think that this iron valency partitioning is likely the reason why different nanophase iron development is observed. And we think this is so because of work that Kathy Dukes et al. In 1999 published, where she space weathered a terrestrial olivine grain that had a rind of oxidized iron around it. And there was a slowed but eventual reduction of iron 3 to iron 2 and finally to metallic iron. And when we inspect the augite lamellae at the rim, we do indeed find more iron 2 there than within the bulk of the lamellae. So it is happening, it's just slowed. So we sort of answered our question regarding the influence of chemistry and structure on nanophase iron development, but also not quite. But in our search, we might have found something truly interesting. Regarding space weathering, it's clear that these exolved pyroxene grains provide such a unique condition for understanding weathering products in natural samples, but we were certainly not expecting the oxidation state partitioning. It's not really heard of. Nonetheless, this was a unique example of a space weathered oxidized phase. And I'm not a petrologist in a strict sense, but my understanding is that until very recently, the moon was considered to be a uniformly reducing environment. However, recent findings of hematite, magnetite, and ferric iron in picritic lunar glasses, along with these pyroxenes, demonstrates that the moon still has some redox history mysteries. Thank you. I will take some questions if we have time.
We do have time if there's any questions for Brittany. This is really great stuff. Love those images of oxidation state of iron.
Thank you.
Yeah, I have a real quick question. So for the time-dependent reduction, do you think this is related to hydrogen?
I do think
slowly moving out, or
I don't know if it's hydrogen slowly moving out. I think because we don't see, there's no structural alteration of the material. We've actually measured the continuity of lattices across the interfaces to see if it was like a more impact related energetics phenomena. This does seem to be solely kind of maybe like a sputtering, like a slow reduction through removal of oxygen.
Okay, all right, thank you.
Mm-hmm.
Maybe one more question?
I've got one. Oh.
This is John Rask. Brittany, did you do any particle size measurements to determine if there's any particle size effects?
So the particles in the pigeonite lamellae are they max out at about 10 nanometers, and we do get more fine population distributions in the augite. So they're there, they're very fine and very small. So I think that their formation is simply slowed because of the higher oxidation state of in the augite.
Well, thank you for your talk. Let's move on to our last long speaker for today. He's Mark Nottingham, and his talk is the Apollo 12 regolith basalt noble gas systematics implications for future exploration. Take it away, Mark.
Hi, everyone. I'm Mark Nottingham from the University of Manchester, and today I'll be talking about a study that was a collaboration between the University of Manchester, Birkbeck College London, and the Scottish University's Environmental Research Centre. There we go. So in the study, we use noble gases derived from individual lunar regolith soil fragments to understand the evolution and impact history of the Apollo 12 landing site by modelling two-stage cosmic ray exposure histories. And to do this, we use neon isotopes and sample-specific bulk chemistry measurements to first constrain the concentrations of neon components present in the gas inventory of each basalt grain, and second, to constrain the cosmogenic gases into production in one of two stages of cosmic ray exposure, with each stage occurring under distinct burial conditions. But first, it's kind of important to understand just how complex noble gas inventories in lunar samples can be. The figure on the right here shows a number of the processes that all affect the lunar regolith to varying degrees. Untangling these processes from each other can be quite difficult. Of particular interest in our study were cosmic rays and the spallation reactions that they cause. So for anyone that doesn't know, the surface of the moon, because it doesn't have an atmosphere or a magnetic field, it's continuously exposed to spaceborne radiation that's collectively called cosmic rays. This radiation flux triggers nuclear spallation reactions within rocks on the lunar surface. And the cosmic rays are broadly divided into two groups based on their origin. So those that originate from the sun are called solar cosmic rays, or SCRs, and they're generally lower energy than their galactic cosmic ray counterparts, or GCRs, which originate from outside of the solar system from sources such as supernova. Importantly, solar cosmic rays only penetrate a few centimeters into the regolith before they're totally attenuated, whereas galactic cosmic rays penetrate to beyond a meter's depth. The rate of production of each isotope depends primarily on shielding or burial depth and the sample chemistry. And importantly for neon isotopes, the production rate ratios between each isotope don't stay constant with a changing depth. This means that if we can isolate the solar cosmic ray produced isotopes from the galactic cosmic ray produced isotopes, they can act as a good indicator of the sample's near surface residency duration. This study examines samples from the Apollo 12 landing site on the southeastern side of the Oceanus Procellarum. Over its history, the site is thought to have had contributions of ejecta from impacts that formed craters like Copernicus, Reinhold, and the Landsberg craters. And subsequently, impacts that formed several smaller named and unnamed craters have reworked the regolith cover that's local to the landing site. The samples we used in the study were 9 individual basalt fragments from parent soil 12003, and they represent a range of different basalt lithologies local to the area. Each soil grain was split into 2 pieces, with one being used to determine the sample chemistry in work published by Alexander et al. And Snape et al. And the remaining piece of the divided grain was then analyzed for its noble gas contents. Before working out the cosmic ray exposure history of the sample, we first have to partition the measured gas into its constituent components. However, our method requires this partitioning to be done without the use of assumed end member component compositions. That's to say the measurements alone have to inform the partitioning rather than the more conventional literature approach, where you would assume end member compositions. To do this, we collect measurements of gases released in temperature step intervals and then model an unconstrained mixing line representing a binary mixture of implanted solar wind and cosmogenic gases that dominate the gas inventory of each sample. We then reduce the Mahalanobis distance of each measurement to basically get the line to fit the data, the modeled line to fit the data as best as it can. That modeled line is assumed to be an accurate representation of this binary gas mix within the sample. And through that, we can then calculate a gas fraction representative of those gases produced by spallation reactions. So for our model, we adopt theoretical cosmogenic nuclide production rate, the cosmogenic production rate model published by Hohenberg et al. Because it provides both solar and galactic cosmic ray spallation production rates. The depth-dependent production rate profile for each isotope is unique. So taking each of those isotopes and combining them into a 3-isotope plot gives us a plot similar to the one that I'm showing here. Just for your information, the numbers on the curve are shielding depths in grams per square centimeter. Given this depth dependence, we can divide the curve into 2 sections, one representative of the sample being buried within 5 grams per square centimeter of the lunar surface in the yellow double line, and one representing deeper burial between 5 and 500 grams per square centimeter in the blue solid line. If we have a sample buried at 65 grams per square centimeter in the regolith, and then any cosmogenic neon produced will show an isotopic composition represented by that red circle that's now plotted on the graph. And if we exhume our theoretical sample from that depth to within 5 centimeters of the lunar surface, where many Apollo samples were collected from, we change the ratios of the cosmogenic gas production so that any gas produced at the surface will now conform to this new composition. And given our samples were collected from the lunar surface, we can assume that they were exposed at the surface for at least part of their existence. Therefore, working in reverse, if we anchor one stage of exposure at the lunar surface and extrapolate a line, that green dashed line, from the value back through the calculated cosmogenic end member value, then the intercept of that line gives us the theoretical production rates at the depth and the shielding depth itself. Our results for the 2-stage models were quite promising. 3 samples showed surface exposure of 6 to 7 million years plus or minus 2. And 4 samples only showed deeply shielded exposure, which means that their surface exposure was at most a few 100,000 years, so below the resolution we can resolve to. 2 samples had mixing lines and cosmogenic end members that didn't fall within the calculated production rate curve, and this likely means there was significant mineralogical difference between the aliquot that is used for the chemistry analyses and the aliquot that was used for noble gas analysis. However, we also can't rule out that these samples were buried deeper than the Hohenberg model is calibrated for. These samples all seem to have been excavated to the surface relatively recently, possibly by an impact such as the one that formed Sharp Crater, which was reported as having an age lower than 10 million years. Those samples with no discernible surface exposure likely derived from one of the recent smaller unnamed crater formation impacts. Our results fall between the ages reported by Bandari et al., and we surmise that the slightly longer surface exposure age that we calculate is a result of our surface exposure model not accounting for depth, the depth being between 0 and 5 grams per square centimeter. It's also possible this is due to rapid reworking of the surface regolith cover, which would be in keeping with the findings of Costello et al. We believe these samples can best be explained by a long period of burial beyond the depth cosmic rays can penetrate to, followed by exhumation by impacts that formed either surveyor or head craters, to a depth where cosmogenic nuclide accumulation could occur, and then followed by excavation to the surface by either an impact that formed Sharp Crater or one of the unnamed craters around the landing site. And because I'm aware of the time, I'll leave those conclusions up there and ask if we've got any time for questions.
Unfortunately, no. We need to move on to the lightning talks, but I'm sure we'll have plenty of time for discussion later after the lightning talks. So Jeff, do you want to introduce them?
Sure, yeah, so I encourage everyone to stay. We'll have discussions after the lightning talks, but now we'll start our lightning talks with Ramon Lachi.
My talk isn't supposed to be lightning talk, and on the schedule it's down as a 10-minute
Oh, you're right. That's my bad. You get 10 minutes. Good catch.
Okay, no, thank you. All right, let me just get my screen shared.
So this is optical monitoring of dust environment around lunar exploration sites. Authors are Lalachi, Glendar, and Stubbs, and Raman will be presenting the talk.
Can everybody see my screen okay? See the slides?
I see a black screen. It says you started sharing, but double click to enter full screen mode.
Oh, right. I'll try just a sec. I'll try it again. Apologies. Okay. Anything now?
Same thing.
Same thing. All right, just a sec. My apologies about this, folks.
Any advice from Mike Tolan if you're on?
All right, I assume you can see a desktop now at least.
Yeah.
Okay, and then if I do that, can you see the slideshow now?
Let's see. Yes.
Okay, sorry about that, folks.
Looks good.
Okay, so with Artemis, we have a new era of human lunar surface exploration coming. The Apollo program showed us that dust is a nuisance and a hazard, being abrasive and potentially toxic to human health. So it would be a good idea for us to be able to monitor it. So to that end, we created models of dust light scattering behavior and distribution for irregularly ellipsoid and spherically shaped dust grains, as shown on the right. The grid covers UV to near infrared wavelengths and grain sizes from 0.01 to 100 microns. Modeling irregular grains is important as most real lunar dust grains are not mesospheres, as shown in the inset electron micrographs on the right and from other people's talks today. We use discrete dipole analysis at small grain sizes and the Hapke equivalent slab with Allen diffraction at larger sizes because of the computational expense of DDA at larger sizes. We then coupled this with a simple dust dynamics model we created to simulate dust raised by activities like astronaut, rover motion, in situ resource utilization and the like. And then we combined all of that in a radiative transfer model to model the brightness of sunlight scattered by an exploration dust cloud caused by these activities. This was basically to answer the question, could you build a camera with off-the-shelf parts with flight heritage as an exploration site dust monitor? And the answer to that seems to be yes. So we can now show a preview of some of the grid scattering properties. On the left, you'll see the scattering coefficient over different size regimes indicated by line steel for irregular grains. The sampled effective grain radii range from 0.05 to 50 microns. Differences in scattering coefficient due to grain size can be observed. Absorption increases dramatically at short wavelengths, so scattering is less and is dominated by the diffraction component. For comparison, we now add lines to the other grain shapes that we tested, prolate spheres in orange and spheres in blue. Differences in scattering coefficient due to grain shape can be observed. Now we present a sample of the normalized scattering phase function over different size regimes, again indicated by line style, and this is for 530 nanometers in the green. The plot shows the dust grain shapes results for irregular prolate spheres and spheres, where the colors are as for them on the left-hand side. It can be seen that smaller scattering angles are a good diagnostic of size, whereas larger angles constrain shape. Larger radiances can be seen at small scattering angles, but this is too close to the sun for a camera really to be practical. From the plots on the right side, on the right-hand side, differences in phase function due to grain size and shape can be observed. There's also variation in wavelength, but this isn't shown for the sake of brevity. We validated our grid against measurements of JSC 1A lunar simulants scattering, where they measured scattering properties by Escobar Cerezo et al. In 2018, and we found that there was a good agreement between our grid and their measurements. So in order to simulate the sensitivity of a notional commercial off-the-shelf COTS hardware camera, we need to model just spatial distribution and abundance across an exploration site, such as a lunar surface base. We created a simple trajectory model for dust launched by activities such as ISRU, astronauts walking on the surface or robot wheels. This uses a Gaussian velocity distribution in accordance with the exploration activities just mentioned. And we set the most probable speed of that velocity distribution to 2 meters per second. This would be for a steady state dust cloud generated by activity at an exploration site, rather than the short-lived instantaneous high density clouds created by these processes. This is analogous to the permanent tenuous impact generated exosphere seen by Harani et al. 2015's results with using LADI, and represents what astronauts would be exposed to on a chronic rather than acute basis. The figure on the left shows our size distribution governed by the power law seen on the right, which is controlled by the exponent alpha. For the purposes of this study, we assumed a baseline value of alpha equals 0.91, which is consistent with the measurements of Harani et al. 2015 and the Lunar ejector cloud. But to see the effects of changing the size distribution, we varied it between 0.8 and 0.99, which are the blue and the orange curves. So using this dust dynamics model, we created spatial dust distribution of dust with a peak value of 1 microgram per cubed at the origin. And this mass concentration scales as Gaussian exponentials in the vertical and horizontal directions from the peak value, with vertical scale lengths of 1.2 meter and a horizontal scale length of about 100 meters. The resulting distribution you can see in the figure. On the left is a cross-section of the mass concentration model across the exploration site, and on the right is where we zoom in to see how the model will be experienced locally. We give the astronaut, surveyor lander, and Apollo lunar module silhouettes for size comparison to the vertical scale of the dust model. Because of the large difference between the vertical and horizontal scale lengths, astronauts and spacecraft would locally experience an almost plane parallel change in dust abundances. Combining all of the previous elements with the radiative transfer model, we simulated sunlight scattered by dust grains at an exploration site. We could then compare the model dust radiances to the detection thresholds of nominal dust monitoring cameras created with off-the-shelf hardware. So here's a sample of our results. Imagine a camera facing the sun that is scanning in elevation above it. The sun is at 4 degrees above the horizon, indicated by the pink sun symbol on the elevation axis. The figure shows the broadband signal to noise, SNR, for the path integrated dust line of sight, varying with elevation angle, using a conceptual camera using the LiSEA-Q PL1 image sensor and a 1-second integration. This is for our baseline scenario using a regular grain with alpha equals 0.91. SNR is shown for the dust model path integrated case, it's the black line, and the case with dust increased by a factor of 10, black dashed line. The thick dashed gray line represents a 3 sigma measurement above which dust is confidently detected and adequate for constraining the dust size distribution. You can see a good fraction of the SNR lines are above the detection threshold, indicating confident detection. To see the effect of changing alpha, the coefficient controlling the size distribution power law, we add equivalent lines for alpha equals 0.8 and 0.99, as indicated by color. Large differences can easily be seen for different values of alpha, so a camera should be able to constrain size distribution pretty well. For comparison, we now add green lines showing the SNR from zodiacal light for a camera placed either at the poles of the equator. The zodiacal light is a potential source of interference, but also a possible calibration source. So on the right, we start off with the same figure as we did for the case on the left, with the regular grains and alpha 0.91 and the 3-second detection threshold, but this time the idea is to look at the effects of shape. So we add the blue and the orange lines, which indicate results for different grain shapes, correlate spheres and spheres, and finally we add zodiacal light again. So although we can see some differences between shapes, shape distinctions more subtle than it was for size distribution, and more information on shape would be obtained if polarization was also measured. In addition to the LiSEA-Q PL1 image sensor results that we showed, we also tested notional cameras using a Symia sensor used in booster cameras and a Hamamatsu CCD, which also gave positive results. So in conclusion, what we've found out, site dust characterization should be achievable using automated simple swivel off-the-shelf camera hardware, even for a highly tenuous exploration dust cloud. Dust abundance and effective grain size are readily measurable with such a camera. Calibration could be achieved using the periodic response using zodiacal light. And current and future work is based on extending the DDA functions of the grid to larger sizes and also including geometric optics. This will allow for the inclusion of polarization effects, which will then allow us to constrain shape as well, better than without using polarization, and we have a manuscript in progress. So with that, I'd like to thank you very much and ask if you have any questions.
Yeah, thank you, Ramin. I think my timer glitched out, so you are perfect with how you timed everything. Does anyone have any questions for Ramin?
I have a quick question. Ramin, in one of your early slides, you showed a slope for dust detectability by grain size. And it looked like the three slopes that you showed, it was very hard to discern different grain sizes in the less than, say, 10 micron or less than 1 micron grain size. Is that correct?
Is that which one? Which plot was that you were talking about?
Oh, it was very early on. It was like
oh, okay, just a minute.
Grain size versus, yeah, that one.
Okay, this one. Okay, so sorry, what's the question?
Oh, so the question is, how well can you deter? Because most of the deaths will probably be in the less than 10 micron grain size, and even more it might be in less than 1 micron. How well are you able to discern those different grain size into fractions?
It seems to, yeah, so it seems to come out pretty, you can see that there's larger differences, but basically as you get, the thing is that once you get up to about 50, once you get up to about 50 microns here, the reason that they're all the same is essentially because we're switching from the DDA over to the Hapke equivalent slab. So they basically all giving the same results. And there's sort of an interpolation between about 0.5 microns, which is the end of the DDA grid, and 10 microns, which is the beginning of the Hapke equivalent slab. So the thing is that there'll probably be more differences at the larger grain sizes than are available here. But until we can basically switch out the stuff at larger grain sizes, we won't be able to tell exactly how big an effect that has, because this is essentially a kludge until we can finish, until we can basically extend the grain size in a better, extend the grid in a better fashion at larger sizes.
Okay, cool, thank you. All right, we'll move on. If you would stop sharing, Raman, great talk. And now we're going to move on to the lightning round. So we have about 4 talks that are 2 minutes each. Our first one is morphologic and spectral characterization of regolith breakdown due to water ice. And this talk is given by Autumn Shackelford. Take it away, Autumn.
Can everyone see my screen and hear me okay?
Yes.
Okay, awesome. So hi, everyone. My name is Autumn Shackelford, and I am a first-year PhD student at the University of Central Florida. And the poster that I will be presenting on is the morphologic and spectral characterization of regolith breakdown due to water ice. And in more common terms, we want to know how lunar regolith is affected both spectrally and in size and shape by the presence of water ice. We would like to understand how water ice exists in and interacts with the lunar regolith environment, specifically how this could impact the geotechnical properties of the South Polar regolith, which is especially relevant in the face of the Artemis program, because tools, rovers, robots, etc., will need to be built to combat the challenges that lunar regolith could pose to them. To begin this investigation into the geotechnical properties of the regolith, we exposed different regolith simulants to different concentrations of liquid water before freezing them. In this poster, we focus on exolith lunar highland simulant, or LHS1, and outline the results of any changes in individual particle morphology and sample spectra for a sample of LHS1 with 30 weight% of added water that was frozen for 1 month, and compare it to unaltered dry LHS1. This poster will be included in the Space Weathering and Regolith Evolution poster session set for today at 9:30 Pacific Standard Time or 12:30 Eastern. I would love to share my research with you, and I hope to see you there. Thank you.
Thank you, Autumn. That was great and well on time. We look forward to seeing you at your poster. Anyone have a quick question for her? I guess not. All right, thank you again. All right, moving along. Our next talk is IRIS CubeSat to measure the effects of space weathering on lunar samples. The talk will be given by Stephanie Connell.
Hi there. Sorry, my camera's not working right now, but I guess I'll just leave that for now. It's unfortunate. I'm just going to share my screen. Okay, and are you able to see the presentation view?
Yep, we see and hear you great.
Okay, excellent. Thank you. Okay, so yeah, my name is Stephanie Connell. I'm a 4th-year undergrad student at the University of Winnipeg. I work for Dr. Ed Klutis at the Center for Terrestrial and Planetary Exploration. So today I'm going to be talking to you about the IRIS CubeSat mission. I'm the science lead and payload manager for the IRIS CubeSat mission. This mission is going to be used to study the effects of space weathering on geological materials in a space environment. And it's the first of its kind with these sample materials. So they're going to be on board a 3U CubeSat, which is the render that you can see here on my slide. It's a very small satellite, and it's going to have an orbital lifespan of about 1 year. It's going to be in low Earth orbit with the International Space Station. So to get into the hypothesis is that visually detectable space weathering occurs on various timescales that are dependent on various factors, such as geological composition and location within the solar system. So this payload includes lunar and asteroid relevant materials that are going to total to about 20 samples on the CubeSat with 4 calibration targets and 2 cameras included for redundancy. And yeah, we're going to study the effects of space weathering with 2 RGB color cameras that are commercial off the shelf to observe these changes in spectral within the visible region and as well the visual. So my poster kind of leans more towards the lunar samples. And yeah, so basically that is it. And please come visit me at my poster. And I'd love to talk to you much more about this.
Great. Thank you, Stephanie, for that cool presentation. Releasing lunar samples back to low Earth atmosphere.
Maybe we can just move on to the next lightning talk, our penultimate talk by Eric Fizzle, post-impact granular dilation on airless bodies. Is he around? Gonna scan the participant list.
If we don't see him, we can move on.
Yeah.
With the last presentation, and if he shows up, we can do a swap.
Makes sense. So last presentation, Danny Waller, investigation of magnetic fields associated with various lunar swirls observed in the far ultraviolet.
All right, is my screen visible?
Yeah, looks good.
Okay, awesome. Hi, everybody. My name is Danny Waller. I'm a second-year master's student at Johns Hopkins working with Josh Cahill. We are doing an awesome fusion of a bunch of different data sets to look in depth at potential weathering effects on lunar swirls, which are both spectral and magnetic anomalies on the moon that there's a couple different hypotheses for why they might be expressed on the surface, but we are focusing on solar wind shielding that could be caused by their associated magnetic anomalies. So we're looking at 2 magnetic data sets, several wavelengths from LRO, and we're trying to figure out if there is a more sensitive data set we could be using to look at weathering across these swirls. I've actually only shown Reiner Gamma here, but my poster has another one. So if you want to see the other swirl that we're looking at, you have to come to my poster session. I'm poster number 13 in the space weathering and regolith section. And something particularly interesting that we've seen so far in our results is the radial component is typically the strongest contributor to the total magnetic field at all the swirls that we've looked at so far. So this is in step with previous work, and it supports this model of solar wind standoff causing the weathering effects seen at swirls. So we're looking at other anomalies, both photometric anomalies and magnetic anomalies with similar geometry to see if there are maybe more swirls out there that we don't see in some data sets that show up in other data sets. Yeah.
Let's see. Thank you, Danny. Does anyone have any questions for Danny? So I have a quick one. I'm a little bit confused. What data sets are you referring to?
So we're using the LRO WAC data set and the LAMP daytime on-off ratio data set in this particular presentation. We're also taking a look at Lyman alpha data sets from LAMP. Yeah.
Cool. Thank you so much. And that concludes, I think, our lightning talks, unless Eric Fizzle is around. And that appears to be a no. So how do we feel about moving on to the discussion section?
I think it's a great time to move on to the discussion session, which will go until 1:15.
Okay.
So now we can entertain any questions that people might have for our speakers, or we can kind of look at some synergy between many or all of the talks. If there are questions that people want to put forward, you can do it in the chat. You can raise your hand. You can even unmute.
I mean, I guess one thing that I could bring up, because I thought it was interesting, just I know myself and Ziyu are both kind of doing MD work. And I just think, you know, sometimes some of these simulation methods are great, but then the problem is that the people who do MD are the only ones that really understand the MD work. And then sometimes its connection is lost to how to project it up to more accurate time scales or more accurate dimensional scales. So I guess, I mean, maybe it's a question for Ziyu or anyone who does modeling similar to that, but, you know, what kind of efforts are put in to try to make sure that what you're simulating has experimental relevance, or we can compare to those? Because I noticed that when I do these talks, often the questions become, you know, have you compared to this experiment, or are you talking about a geological scale? And then the answer often becomes, no, I'm talking about like a picosecond scale. So it's a huge gap. So I just think thinking about how we can tie simulations into experimental and then ultimately actual lunar data, I think is an interesting concept. It's just a thought, I guess.
So Liam, I want to follow up on that. So it was very unclear in either of the simulations what potentials were you using, because in the end the interaction potential is what is very important, and you were looking at different targets, so the interaction potentials were likely not be the same. But could you comment on that?
Yeah, definitely. So I guess your question is totally relevant, because I think for any MD study, the interatomic potential is basically the crux of whether it's going to be accurate or not. And I think one of the challenges in talks like this that are not specific to MD is to try to decide how specific you get into MD related topics without kind of losing the audience. From the point of view of mine, what I used was a reactive potential. So it's a REACT-FF. I used the same one for all my models. I think that's important in the sense of you want to make sure that the differences you observe are not due to just changing the potential type, and you want to do some kind of a verification. So the potential that I selected had already been verified for silicates, sodium silicates, and silicates containing hydrogen, and both for amorphous and crystalline. And just for the group, I guess those are often verified compared to experimental or density functional theory data. So DFT data is probably like a scale down. So yeah, that was the interatomic potential I used. And I guess, and the other thing that I could note is that when I talk about discrepancies found in previous results, one thing that's important to note is that all those previous MD studies that I showed also use the same potential that I'm using. And that was an important flag for what's going on here, because often when you see a difference in simulations, it's often the parameters used, and typically in MD, that's ultimately that we used a different potential than them, so our results were totally different. But when I saw that all those studies used the same potential, then that flagged for me that there's something going on in the methodology or some reason why we're seeing these like orders of magnitude difference. And ultimately, I believe that that's essentially not accounting for the diffusion mechanism, because we often think of diffusion as this constant motion. We sample for long enough, we'll get it. But if the diffusion is just intermittent jumps, which at low temperatures are very, very rare, then you have to sample for long enough that you're observing enough jumps that you're not at the mercy of just statistical sampling. So I guess that kind of hopefully answers your question a little bit.
It answers it quite well. I have a little bit of a follow-up. So we're looking at this problem with respect to hydrogen buildup in glass waste forms for radioactive storage.
Sure. Okay.
Turns out that the barrier heights for motion and proton transport are not the standard lattice vibrations that you would consider. It's actually the dangling OH bonds that are formed, and then you get these layered structures in a lot of the glasses, or within the pores, like we're being discussed with the ice, and so those subtle structural differences actually govern the energetics. Is there a way for you to sort of put that in as a next step?
Yeah, definitely. So I guess the key there is when you talk about dangling OH bonds and things like that, you're essentially talking about traps and you're talking about reactions. So the key is to use an interatomic potential that can allow for bonds to form and break, and you're not just at the mercy of something that's kind of fixed. So I think there, yeah, definitely, because what you're basically referring to, you're essentially saying, I think at least, is that the energy or the activation energies that need to be overcome, you're seeing are heavily dictated by these dangling bonds. So yeah, you just need to simulate with something that can allow these bonds to form and break. So yeah, I think so. It shouldn't be a problem.
All right, you had posed, Liam, a question to Zhu. Zhu, you want to respond?
Sorry. Yeah, thank you so much for the question. Like, first of all, the timescale problem, I think that's pretty important because usually, like in planetary science and also in astrophysics, astrochemistry, usually the timescale is like million years. Well, we have the molecular dynamics simulation in this timescale, picoseconds or even femtoseconds. Yeah. So what I think we can do is to limit some, create some like artificial conditions, or like using some trick to simulate those kind of like space varying process. Like for example, when I was doing like implantation process, for the specific area I used for the sample is only like about like in the scale angstrom square. Yeah. So if you consider the flux of the solar wind to the PSRs, so usually there's only one implantation per day. So if you make sure you relax the surface to the original temperature, then the implantation and relaxation could represent 1 day. Yeah. So in this way, you can like continue in the implantation process, and making sure each implantation won't affect another the other implantation process. Then you could like simulate like a real planetary science time scale.
Yeah, definitely. No, that makes sense.
I mean, for other cases like micrometer impact, well, you know, for like 20 kilometers per second impact, the hypervelocity impact usually occur in a really small time scale, and I'm not sure if experiment can capture the impact process in about like picoseconds or even microseconds, but MD simulation can definitely capture the whole process. So I would say that's a good thing about MD, but another thing is like the relaxation time. Like, how long do you wait for the MD for the impact to relax? One thing I would do is like monitor the temperature. When the temperature is lower than the absorption temperature of water molecules, like 170 Kelvin or even lower, then I will say the relaxation is almost done. But honestly, I think that could lead to some error, but it could be some approximation. So
yeah, no, yeah, that makes sense to me.
Yeah.
When you're doing your impacts, I guess just one thing to add to that is that when you do your impacts, first is, are you tracking the sputtering too? And then the second thing, which I presume you're probably already doing, but you can use a dynamic time step.
Yeah, that's right.
Actually, let the time step modify, so you like limit the amount of motion between each step. That's just an MD specific idea that I'm not sure if you thought of. Yeah, and Micah, I know your hand's up there, so
yeah, I was gonna say Liam and Zhu. Let's go to Micah. I don't know if the question is you guys but probably is. Micah, you're mute.
No, sorry, I was just playing with the reactions a little bit too much. I think I got a little overzealous there. My question was actually for Brittany. You talked about this a little bit in the chat, and I was wondering if you could go into it just a tad more on how you think that this nanoferrous iron might be forming sort of deeper in the sample, sort of below the rims. I think you sort of glossed over that a little bit in the chat, and I was wondering if you could go into it a little bit more.
Yeah, thank you for your question. It's truly unusual that they're forming that deep, because our conventional understanding of the implantation depth of helium and hydrogen is like 10 orders of magnitude smaller than that. So like maybe up to 35 nanometers. And Morgan brought this up, but there is that study, Quadri et al., 2015, 17, talked about the diffusion of oxygen being anisotropic in pyroxene, and it's different in an orthopyroxene versus a clinopyroxene. And so one of the things I was curious about was to determine the orientation of these lamellae, because if we can determine kind of the orientation normal to the space weathering, we can figure out if oxygen is diffusing through and healing where hydrogen is getting to and kind of running into and forming and kind of nucleating the nanophase iron particles. So this could be a crystallographic effect. There could be ion channeling that could be bringing hydrogen deeper into the crystal. So yeah, this is a really interesting and weird texture that we saw.
But it seemed kind of clustered too, or was it really widespread? Is that just the image that it looked clustered in?
It might have. That's a good point. It really just kind of seems like bubbles almost forming like underwater and kind of like floating to the surface. They could be clustering. You could be getting like localized areas of like hydrogen nucleating bubbles, and then all the iron around that could be getting reduced. So yeah, we're not quite sure. What we would need to do to really test that would be to look using high resolution TEM to look at and if there's any local crystallographic like amorphization or structural changes in that area that would cue us into what was happening at an atomic level.
Cool. Okay, great. Yeah, thank you.
Thank you.
I had a question for you too, Brittany, while you're on. So between comparing the high calcium and low calcium pyroxene production of nanophase iron, is there a mineralogical or structural control at all that's also in play with them having different structural mineralogies? And does that give you any clue to how olivine might space weather in relation to pyroxene?
So between the high and the low calcium pyroxene, so the fact that there is iron 3 in an augite is not weird. It happens terrestrially. It can contain up to like 60-70% weight percent iron being ferric. It hasn't been found in a lunar pyroxene before, and I want to emphasize, and this maybe kind of gets into Shuai's follow-up question about this is primary ferric iron. We think it comes from a magmatic source, but the high resolution of the technique, these are only 20 nanometer wide lamellae, so we might not have detected it. It's just a detection limit thing. So the iron is maybe in a different crystallographic location in the augite than in the pigeonite. So like the M1 versus the M2 site, so there could be like cation site ordering, and because the M2 site is a 8 coordinated versus the M1 is 6 coordinated, so there could be anisotropy effects occurring there. But with olivine, it's kind of like sterically limited in its ability to incorporate ferric iron, and so I think it would have a more isotropic space weathering effect. And so I'd be curious to analyze other minerals that have structural anisotropy to see if they have this effect with iron.
Cool. Thank you.
Can I have a follow-up question, which is related to both, maybe all three of these? So the radiation chemistry community actually uses high doses of ionizing radiation to produce nanoparticles. And they can produce iron nanoparticles in a number of glasses containing iron oxide. So are you sure that they're, because of the dose rate with TEM is so high, are you sure that that's not happening at any level?
I would expect to see it happening everywhere. So the fact that it's not occurring in the pigeonite and it would just be happening in the augite would be a little strange, but the adjacent augite, that unexolved one I shared, didn't have any, or it had very little ferric iron compared to the exolved grain. So although they're adhered to one another, I'm not sure they have the same magmatic origin, but we do, you can certainly get beam damage in the TEM environment, but because we don't see kind of it happening ununiformly, and if we park the beam and scan across an area, we're not seeing any migration of these elements and evolution of the material. So we need to let it scan for a long time to really see oxidation effects like that.
Okay, all right.
I see what you're saying, yeah.
Thank you.
Thank you.
Shuai has his hand up. Do you have a question?
Yeah. So thank you for the answer. The rest part of my question is like, I didn't pay attention. Did you do the experiments for Brittany? Did you do the experiments in a vacuum, like oxygen free, or have you considered like a contamination of oxygen from the atmosphere?
So the high vacuum environment of the TEM does theoretically exclude oxygen, but it does, there is always a small amount of oxygen that could be occurring, and also the material could be degassing, although we do bake it prior to introduction into the TEM or degas it, so that we're not introducing any impurities. And I'm sorry, what was the second part?
No, I mean like when you did the space weathering, like radiation, irradiation, did you do it in a vacuum or in an ambient condition?
These are natural samples. These are return samples, so these are not experimental.
Oh, sorry.
Yeah.
I misunderstood. Okay, thank you.
Yeah, you're welcome. Thank you.
How about any questions for Mark Nottingham on cosmic ray exposure ages, or Raman Lachi on optical monitoring of dust? Any questions for them?
I have a silly one for Mark. Does your analysis process destroy the samples?
Yeah, it is destructive. So we split the sample, the grain initially from the soil, kind of basically mechanically fracture it as best as we can down the middle, take one part, and that's non-destructively analyzed for the chemistry. But the other part would basically heat it up in a vacuum furnace to release the gases from it.
And I imagine you wait for quite a while until you're pretty sure that all the gases are out. And then...
Yeah, so I think our analysis procedure was to basically heat it for 20 minutes. And then the gas that's released goes through kind of various processes of purifying it, taking out active gases that we don't want, that would interfere with our measurement. So yeah, I think for those samples, it was about 20 minutes that we heated them.
Thank you.
I had a question for you too, Mark. You had mentioned that the overturn rates at Apollo 12 were more significant, and I guess that's more significant to other Apollo landing sites. And I was just wondering how you compared it being more significant than other Apollo landing sites. Did you, in the past, make measurements on other Apollo landing sites or literature data, or is it really, it was just higher than other measurements at Apollo 12?
So I might not have explained that particularly well. It's not that the overturn rate is particularly high at the Apollo 12 site, but that work that I mentioned, the Costello et al. 2018, I think, they basically found that secondary impacts, so you have the primary impactor that forms the crater, and the material that's released from that forms secondary craters as well. And those secondary craters are far more important for the overturn rate. It basically revised down the amount of time that it would take to completely homogenize a given thickness of the regolith.
Okay, so you're actually seeing this gardening by secondary impact craters.
Yeah, they seem to be far more important than certainly the previous models had suggested or accounted for.
Neat. I like it when data can, help models, and models can help data.
I was very happy when our results lay between those values.
Any other questions for our speakers? We can even entertain questions for the lightning talks. Quiet group on Thursday. We don't have the usual LPSC coffee or NESF coffee to get people awake.
Well, while people are thinking of questions,
Yeah.
an announcement by Mike that the plenary talk from this morning continues during our break. So if you're interested in Ryan Watkins's talk about maternal walls in STEM, then head over to the plenaries in 5 minutes. Did Tom have a comment?
Yeah, it was a question to Jeff. Can you give me your opinion on how useful the PCA approach is? Because there's a more sophisticated machine learning sort of algorithms out there. So I'm just sort of wondering, the question is, how good the data sets are and so forth for machine learning. I'm just wondering what your general opinion is on that.
Well, we use PCA, it's a great technique for, taking multispectral data and, looking at trends that, aren't apparent. With just multispectral data, it's easier to, look at those full spectrum. Machine learning could be the next step on the principal component analysis, but, someone's got to do the machine learning. There are, plenty of spectra out there that you could get from eLab and other databases that could start. And I'm sure that would be actually a great project for undergraduate or grad student to begin with. But both PCA and machine learning have, the fundamental flaw is, crap in, crap out. If you don't understand what you're putting in, you can get unrealistic answers coming out. So we, been using, with PCA, testing what our components are, the best we can to make sure that, they align to something in the spectra and that we can interpret those changes in spectra with, the geologic process or space weathering process that's happening. So I think there is room for machine learning. It's just that it hasn't been, my expertise, and someone has to step in to do it.
Okay, thank you.
I have a question for Liam. In your simulations for diffusions, could you clarify if you considered the near surface electric field on the moon?
So we didn't simulate protons as much as we simulated neutrals. So we didn't apply an electric field because in speaking with my co-authors, basically most of the ions become neutralized once they make their way in through the surface. So we didn't as much look at the effect of the electric field, no. But now, with that said, the potential used, the reactive potential, does deal with the equilibration of charges. So any charges that would build up would be accounted for within the potential. But we didn't start with an ion per se.
Okay, thank you.
Or a proton, I guess, yeah.
And a quick question for you too, Liam, some people have used Monte Carlo simulation to do similar analysis. Can you compare, Monte Carlo versus the analysis that you're doing?
Yeah, so I think that's actually a really interesting comment. So, because one of my co-authors for this work is actually Dr. Farrell, and he's done a lot of the Monte Carlo work on diffusion of protons. And I guess the difference between MD and Monte Carlo is Monte Carlo, because it often uses distributions of diffusion coefficients and activation energies, it's kind of at the mercy of what you give it as an input. So I think what the purpose of the MD is to better inform the inputs of the Monte Carlo so we can better constrain what we expect the diffusion coefficients and the activation energies to be. So the limitation of MD is that it's so computationally intensive that you'd never be able to approach the scales you can approach with a Monte Carlo work. But if you can better inform the inputs of Monte Carlo such that you better understand the actual mechanisms going on, then you can make your Monte Carlo more accurate. So I think that's kind of how they connect.
Okay, cool, thank you. I was wondering how that worked.
Yeah, sure, no, yeah, of course.
And now, perfect timing, we've come to the end of our session. Thank you to all of our speakers, and it's been a pleasure.
Yeah, thank you to Carolyn and everyone who put the plan together, this session together, and for our SSERVI central help.
Yeah, it's been great discussions and super active in the chat, which I always love to see. So maybe I'll see you guys in the plenary, or if not, the poster session later today.
Great.
Yeah, thanks, Jeff, for co-hosting too.
Yeah, thank you, Alicia. It was nice to meet you.
Recording stopped.
And you have 4 minutes, including the 2-minute questions, and then 8-minute announcements are also going to be done. So we will have this timer on the screen. John's going to do this for us. And you can also track your time doing this, just pin his video. We don't have any lightning talks in this session, so it's going to be just the 8-minute presentations. And after the session, we will have a longer discussion period, and we can also talk about every topic and also discuss some presentations that we didn't have time to make some questions and answers. Participants are asked to stay muted and keep their video cameras off unless called. And if you want to put some questions on the chat, remember to use the Q mark in brackets, just to be easy for us to see your question and properly address any question or comments. We also ask that respecting intellectual property rights of each presenter by not sharing screenshots of their work without permission. And participants should be free to close the chat window if it's distracting. And we can also inform an important announcement. Thank you.
Great. Well, it's 11:16 now, so we're close to staying on schedule. What we'll do is we've got a series of some really interesting talks here today. My name is John Rask. I'm from NASA Ames Research Center, and I invite you to ask questions in the chat, and of course can participate in the, as Douglas mentioned, in the discussion session at the end. So our first speaker is Douglas Fontes, and his talk will be on lunar regolith particles interacting with a lander rocket plume at low altitude. Douglas, please take it away. You have 10 minutes.
Thank you, John. So this is the title of my research, my study. Thank you for the introduction. And this study was also made in collaboration with Philip Metzger and James Montavani. So why should we investigate rocket plume interacting with regolith? Essentially because of issues associated with damaging structures around and also crater formation. Numerical modeling can provide key information about the velocity and angle of the ejector that can be used to design effective ways to reduce potential damage caused by the descending of the lander on lunar surface. In comparison with previous lander sizes, larger landers intended for human landing exploration on the moon, we will have higher momentum of the rocket plumes as well. That's going to directly influence how the dynamic forces act on particulate, which also affects the erosion mechanisms. The higher energetic flow increases the potential for damaging nearby structures and the lander itself during its descent. The main goal of this study was to investigate numerically particle trajectories under the influence of a 40-ton lander at different altitudes. The particle diameters ranged from 1 micrometer to 1 centimeter. And the initial radial position of a particle ranged from 1 to 10 meters from the center line of the rocket jet. To obtain some insights of the realistic interactions between rocket plumes and particulates on lunar environment, we simplify the problem to a physical model defined by some hypotheses, boundary and initial conditions, as well defined fluid, environmental, and particulate properties. This simplified model is then represented by appropriate transport equations and correlations that can be solved using a numerical model. The numerical solutions returns information that can be used to better understand the interactions and properly act on technological issues to reduce the risk of damage due to the ejecta. So in this slide, we have the velocity, magnitude, density, pressure, and temperature fields of the rocket plume. These figures are a longitudinal plane in the mid-angle of the quarter domain, where red color represents high values and blue color represents low values of the shown variables. In the top left corner, we have the velocity magnitude of the rocket plume at different altitudes of the lander. So we can see that there is a shock waves in a bowl format beneath the nozzle exit for all altitudes except for a lander at 1 meter. In the top right corner, given the logarithmic scale, we can observe how fast density as well pressure reduces with radial distance from the center line of the rocket jet. These reductions in the gas density and pressure limit the drag force effect on the particles to a certain distance that does not exceed the numerical domain. The rocket plume temperature indicates the local level of agitation of molecules that influences how they transfer momentum to a particle. As we can see in the boundary layer and in the shock wave, the molecules are more energetic, which allows more momentum transferring from the flow to the particles of the regolith. Due to the drag force, regolith particles will be ejected from their initial positions, reaching high velocities according to the crossed plume flow region. When particles leave the numerical domain, the drag force is negligible because of the fast plume expansion, and those particles will follow basically ballistic trajectories only. Pressure and shear on the bottom surface are important measures to quantify possible erosion and particle lifting mechanisms. In these plots, we have top views of the bottom surface of the numerical domain, where each quadrant corresponds to a different lander altitude. The levels of shear stress and pressure varies with altitude. The lower is the lander altitude, the higher the pressure and shear are. As we can see, the pressure is maximum at the corner of the domain, while the maximum shear stress occurs at a certain radius from the center line of the rocket jet. This is due to a combined effect of the density and the velocity in the boundary layer for the shear stress. These figures show particle trajectories plotted on a longitudinal plane X and Y. X represents radial distance from the center line, and Y is a vertical distance from the bottom surface to the rocket exit. In the left side, we have particle trajectories for a lander at 1 meter in altitude, and in the right side, particle trajectories for a lander at 7 meters in altitude. Different colors represent particles initiated at different initial radial positions. Particle trajectories change in this animation for different particle diameters from 1 micrometer to 1 centimeter. Particle trajectories present lower angles when the lander is at 7 meters in altitude compared to the angles when the lander is at 1 meter in altitude. Also, larger particles are more likely to bounce than smaller particles, even inside the numerical domain. Just a reminder, the numerical domain in this case is 20 meters radially. In these figures, we plot the velocity magnitude of particles leaving this numerical domain. Each curve represents the variations of velocity magnitude with particle diameter for a specific initial position of the particle in the domain. In the left side, we have particle velocity curves for a lander at 1 meter in altitude, and in the right side, we have the same plot for a lander at 7 meters. The velocity of a particle leaving the numerical domain depends on its size, initial radial position, as well as the lander altitude. Particle velocities are higher when the lander is at lower altitudes. The maximum particle velocity predicted in this study was around 750 meters per second, when the lander was at 1 meter in altitude and particle size was 1 micrometer. The maximum velocity found in this work is below the lunar escape velocity. However, ground surface, including craters, may affect the plume flow, leading particles to high velocity regions of the plume. Particles that go to those regions would reach higher speeds than the lunar escape velocity with greater damage potential. So final remarks, basically, this work provided information about angle and the velocity of the eject that can be used to estimate potential damage to nearby structures and develop strategies to mitigate damage caused by the ejectant. Particle velocities highly depend on the characteristics of the lander size, altitude, and the regolith size and position. The maximum velocity in this case was below the lunar escape velocity, but we need to remember that different soil topology and also mechanisms of rolling and bouncing may take particles to other plume regions with higher velocities. And a Randy correlation for particle velocity was developed is on a paper submitted to the Astronautical Journal. Thank you for your attention. I'll be glad to take any questions.
Great, thank you, Douglas. Does anybody have any questions? There's one in the chat. Do you use a CFD and or DSMC code to compute the gas flow? Sorry if I missed this, but also could you say a bit more about the boundary conditions that you assume at the lunar surface?
Yes, I removed some slides because of the time, but yes, I used the DSMC code to solve the rocket plume flow. And in terms of the boundary conditions, we had like wall surface on the bottom surface and symmetry planes for the quarter domain of this 3D numerical domain. And to represent this near vacuum condition, we had a high speed velocity in the outlet flow of the radial outer surface of the numerical domain.
Great, thank you. And there's one question in our time remaining from Michelle Monk. Was the surface always assumed flat regardless of altitude?
Yeah, that's one thing that we need to explore. But in fact, we assumed that the surface is flat in all conditions, but that's not it's not true for the real case. So we want to understand to model this using maybe dynamic mesh with the DSMC code to be able to simultaneously have the gas flow producing some crater during the descent. But we are working on this yet.
Great, thank you. Well, thank you. Good questions, right on time. And now we'll move to our next speaker, Dhaka Sapkota. And Dhaka will give a talk on gravity scaling of the cratering mechanism by a cold, turbulent subsonic jet. Dhaka, please, you have 10 minutes.
Hi, everyone. I hope all of you can hear me well. I will again be talking about the cratering mechanism, just like Douglas did, but this time I will be talking about based on some experiment that were done in the past, and then I'll try to connect all the physics behind the cratering, the erosions to the gravity. And my co-investigator on this are Phil Metzger and Marla Philippe from Florida Space Institute at University of Florida. Going into the experiment, I'll try to set up some relevance to the work, and the relevance comes from the physical state of the space. As we heard many times in this conference, the surfaces of the moon and Mars have a dusty layer of granular regolith. The engine exhaust from the landing spacecraft blows away the regolith, and then it changes the environment physically, chemically to the long term. It can also sandblast the hardware within reach. And then as Douglas also mentioned, the particles can even reach to the escape velocity. So it's really important to understand the erosion during the landing. And then per this, we use the experiment that were performed quite a bit time ago, about 10 years. And then, but the data were never analyzed. So we went back and then started to do the analysis. The instrument was called the HUSH, the handheld observations of the scour holes. As you can see on the top right, it's an enclosed transparent chamber with a sand bed inside. The fan circulates the air within the chamber going through the flow meter. The nozzle is divided, it's splitted by a bevel wall so that we only see only the 50% of the gas will make the crater. So if you look at the front view from the below, we see the vertical dissections of the crater, which can be recorded. Those experiments were recorded as a video file. Different variations of the variables were used, such as jet speed, different sand types, and the gravity levels. We analyze the data and present with some observational and analytical results here. Going to the observations, there are a few distinct erosion patterns that we observed, that we call them a bearing capacity failure. This is the term widely used in the engineering. When the stagnant pressure of the jet breaks into the sand, this happens to during the beginning or the intermediate stage of the cratering. Then after, we observe what we call the diffusion-driven shearing. It happens during the intermediate to the final stage of the cratering. The gas diffuses through the soil, induces the drag force throughout the bulk of the soil. And then at the end of the cratering, we observe what we call the repose erosions. It starts from the intermediate stage and goes to the final stage. The exiting gas from the crater soaks up the sand from the top of the crater and makes a conical top. On the right, here's a video I will play. It's from the ground-based experiment. On the left panel, you will see the crater growing. And on the right panel, you will see two plots, the red dots for the volume, and then the triangular black dots are for the crater depth. Okay, I'll stop it here. The conical part is not seen here because it's all cloudy and dusty there. But one really interesting pattern we observed in this plot is that on the crater depth, even if the crater depth stops growing at about 4 seconds for this experiment, but if you look at the volume, it keeps growing. That means the erosion is erosion is happening within the constant rate even after the depth is stopped growing. This is because the contributions from the diffusion-driven sharing. Now we move on to the experiment that were performed on the reduced gravity. Here we take the set that was performed for 250 to 300 micron sand. On the left, we see the plot for volume versus time at different gravities, and then gravities increasing from top to bottom. On the right, we see the similar plot for the depth. And as you can see here, as we go higher in the gravity, the erosion rates are decreasing. But one thing we need to notice here is that, for example, for two gravity levels here, the bottom two curves, they were supposed to be the same. There is a gap there, which comes from the experimental error. And then for that, we have a repeated experiment, and then we will try to minimize the errors from there. Similarly, we looked at the Martian simulant. Here, nothing out of ordinary. They all follow the hierarchy of the gravity, and then the constant increase of the erosion rate, as I explained in a couple slides ago, is also followed nicely here. Then finally, we looked at the coarse Martian simulant. Here, there's one more unique feature that we observe here. As we go higher in the gravity, there is a clump. The erosion is also clumped in a band, and then the depth is also clumped in a band. This is because when we go higher than a certain point of the gravity level, there is no real distinctions. The erosion saturates. Now, after that, we went back and then tried to scale the gravity for the first set of data that we analyzed. So what I did here is that I scaled the volume with the square root of the gravity, and then try to fit with that with the functions here, a constant times log of b, another constant times the time plus 1. Here the parameters A has a unit of the volume divided by the square root of gravity, and then the B has a unit of the inverse of the time. As you can see here, the fit is not that great. The gravity scaling converges the data in some extent, but the uncertainty in the fit parameter indicates that there are other variables involved. So to get the real conversion, the real scaling of the erosion rate, the scaling of the gravity is not enough. We need to parameterize all the variables involved in the erosions. So with that, we have come up with some hypotheses. If we have to express the erosion rate on this function, then the parameter A, this is just a hypothesis, may be explained with those variables. On the numerator, we have density of the gas, the velocity of the gas, the size of the nodules, and then in the denominator, we have density of the sand, size of the particle, and the gravity. So if we can parameterize all these parameters individually, then only we can scale the erosion rate properly. Similarly, for the time, it's less known. This is just my idea here. We need to investigate more. So what we hope to do at the end of this work is to develop a complete comprehensive expressions that connects the physics that happens in the cratering experiment. And with that, we hope that it will help to calculate the effect of the space shuttle landing and support the scientific integrity. That is my conclusions. And if there are any questions, I'll be happy to answer. Thank you.
Thank you very much. In the interest of time, we'll move to the next presentation. We'll be able to answer questions in the discussion period. Our next speaker is Benjamin Farr. Benjamin will give the talk, Design and Performance Considerations of Graphene Laminated Thermoplastics for Electrically Conductive Applications in Space. Oh, I'm sorry, I've read the wrong one. Benjamin is giving the talk on electron beam dust mitigation method for lunar surface exploration. My mistake. Benjamin.
All right, does everybody hear me? Okay.
Yes.
All right, thank you everybody for coming to listen to my experiments of dust mitigation for lunar surface exploration. I'll be talking about several experiments that we've done, actually. So, hang on, let me make sure. Okay, cool. So the motivation for the experiments is, of course, lunar dust regolith has been shown to be an issue for lunar exploration. It causes damages to spacesuits. It causes issues for solar panels and thermal radiation. It causes issues with mechanical equipment, and it can also cause issues for just astronaut health. So we'd like to get rid of that dust, and that is what me and my team have been working on for the last couple of years. So our theory is our experiment is based on a theory called the patch charge model. And the patch charge model was developed to explain electrostatic dust lofting due to solar wind exposure and UV radiation. So the theory postulates that if you have a dust layer, there are microcavities between all the dust particles. And when the dust is bombarded with UV radiation or solar wind, that generates secondary electrons or photoelectrons that are emitted from neighboring particles, and those build up inside those microcavities and eventually gives you a really large negative force, which then forces the particles to jump away from each other. So that's what we're basing this dust mitigation method on. So our experiment, we are using a hot tungsten filament to create an electron beam, and we are just shooting that beam at a dust-covered substrate. And we've tested everything inside of a vacuum chamber where we feed in about 10 to the minus 4 torr of gas just to create a plasma background for the electrons to actually travel through. In the first experiment, we were trying to figure out a whole bunch of things. We're trying to figure out the optimum beam parameters. We were trying to figure out how different materials react to this cleaning method. We were trying to figure out, how the initial thickness of the dust layer impacts everything. So we just wanted to understand if this is actually something worth pursuing. So the setup we have inside the chamber, we have our dust covered sample tilted 45 degrees to the filament. And then to record the data, we just record a video of it and we analyze that video data. And here's a quick video just to show how much the dust actually reacts to an electron beam. So that is the dust hopping around. And then these images here show a before and after shot of a glass slide that was covered in dust. We expose it to the beam and now it is no longer covered in dust. So that's pretty cool and good results for us. So the first test, we wanted to see the current density and how that affected the cleanliness. And we found that for anything above about 0.3 microamps per centimeter squared, we get the same final cleanliness. The only difference is the cleaning time. So for all the tests after that, we ran about 1.5 microamps per centimeter squared. We also tested the beam energy. We tested 8 electron volts, 150 electron volts, and 230 electron volts. And we found that it actually does get a little bit cleaner every time we increase the voltage. We tested glass and spacesuit materials and found the glass was a little bit easier to clean than the spacesuit. And we believe that's because the spacesuit has a whole bunch of little pockets for the dust to get inside of, so it's just a little bit harder to clean. And then we also tested the initial dust layer thickness. So we tried a thin layer, a medium layer, and a thick layer. So 0%, which is completely covered, 40% clean, which is about 60% covered, and then 60% clean. And we found that the thicker the dust layer is, the harder it is to clean up, which kind of made sense to us. So this is just a quick slide going over the results. I'm going to skip over that pretty quick. Our current experiment that we're working on is trying to optimize the results even further. So everything we found in that last experiment showed that we could get about 80% cleanliness. So we wanted to try and get rid of that last 20%. And we were hoping that to get rid of that last 20%, we can rotate the sample relative to the beam source, which would change the angle between the beam and the dust. And the idea is that allows different microcavities to be exposed to the electron beam, allowing us to just clean off more dust. And we did do some preliminary experiments, just rotating the sample without a beam to show that no dust falls off just based on the rotation, the vibrations, the gravity, and nothing fell off, so that's good. So we're confident that any increase in cleanliness is just because of the changing angle. The only thing that we changed for this experiment was that we attached the sample to a DC motor that rotated it at 6 RPM. We would rotate for 2.5 minutes, exposed to the beam, and then stop for 2.5 minutes. And in that 2.5 minutes pause, we would take our data. And we tested glass first. And for every test, we would let the process go without rotating. Then once it stopped, then we would start rotating so that we could see exactly how much the rotation helped. So for glass with a thick layer, we found that we got an increase of about 20% with the rotation. So we jumped from 60 to about 80. And then for a thin layer, there wasn't really too much increase with the rotation. And we think that's just because it was already so clean in the first place. Pat ourselves on the back. So for the spacesuit, we found that for a thick layer, we also get about a 25% jump in the cleanliness. So it jumps from about 55 to 80. And then for a thin layer, we go from about 65 to 85. So both cases, that's good. We see some sort of increase in the cleanliness when we start the rotation. And then we also tested a photovoltaic solar panel with this rotation method, and that wasn't quite as good. So we found that for a thick layer, we get about a 10% increase from maybe 45 to 55%. But then for a thin layer, we don't really see too much change at all. And that's just because the actual solar panel is very, very adhesive to the dust. And we have yet to discover why. That's something in the future. So to summarize real quick, we're very happy with our results. With the rotation method for glass and spacesuit, we're able to get about 85 to 90% cleanliness, which we're very happy with. The solar panel was not as good. We got about 63% max. So we still want to work on that a little bit. Yeah, and then for our future experiments, we're going to continue testing other materials. We're going to test ITO, we're going to test a thermal blanket, Kapton tape, aluminum, stainless steel, and really anything else that we can think of that might be worth testing. We are also going to look into testing, instead of rotating the sample, we're just going to set up multiple beam sources. That way we can simplify the experiment a little bit and just have different beam sources oriented differently to the sample. And then way in the future, we're also going to test if this method works for mitigating Martian dust. So that is going to come in a couple of years. That is all I've got. Thank you very much. I can answer any questions if you've got any. If not, thank you.
Very interesting. Thank you, Benjamin. Nice talk. I don't see anything in the chat right now, and encourage people to pop questions in there. I do have a question for you. Yep. I may have missed this, but can you tell us a little bit more about how you prepared or distributed the dust on the surface, and did you do anything in terms of sifting or grinding or anything like that to prepare your specimen in advance of the study?
Yes, sorry, I was trying to rush through all these slides and I forgot that part. But yes, so all of our tests, we did them with a JSC1 lunar simulant that was sifted down, so it was all less than 25 microns. And then to deposit the dust onto the sample, we just sift it straight onto the sample to try and get it as evenly distributed as possible. And then as far as determining like the initial thickness of the layer, we wrote a program so that we can just take a picture of the background, then take a picture of the dust layer, and then that'll tell us how thick we're starting out. Yes.
Great,
sorry.
Thank you. No, that's very good. And if you mentioned it, I missed it because I'm juggling a bunch of things here. We do have one more quick question. One of them is how are your cleanliness percentages calculated and how much power is required? Do you want to take a stab at that?
Yeah, so the cleanliness percentage, we calculate that just by an image subtraction, basically. So we take first a picture of the completely clean sample, and then we take a picture of the sample completely covered in dust. And then we use those to basically subtract the images of the sample throughout the test. So we take a picture every 1 second, and that's how we got those plots. So every frame we have the test data, and then we compare that to the clean and the completely covered data, and then that gives us our total number. And it works well for glass and spacesuit because the glass we just put on a white background and the dust is gray, so that's a pretty good contrast. Same thing for the spacesuit. Some other materials we're testing, we might need to come up with something different because like thermal blanket is basically just orange foil. So that doesn't have a very good contrast. So we're struggling with that right now. But yeah, it's just an image comparison.
Great, thank you. Well, now we'll move on to our next speaker. Thank you, Ben.
Thank you.
Our next speaker is Zach Siebers. And Zach will present design and performance considerations of graphene laminated thermoplastics for electrically conductive applications in space. Zach, you have 10 minutes.
Excellent, thank you. Can you confirm that you're seeing the slides?
Yes, sir. Awesome.
Yeah, so thank you everybody for joining me this afternoon or maybe closer to lunch, depending on where you are in the world. I'm excited to be here to talk about some electrically conductive composites we've been working on and some of the applications we think they might be useful for in space. So first of all, I want to highlight the unique nature of this program it straddles the interface between material science and space exploration, and that's enabled by the REVEALS research program where we look at a lot of different research areas, from astronaut HUD systems, which I don't think is being talked about at this particular gathering, but has been in the past NESF meetings. We have some ideas or research going on around novel radiation shielding composites, scalable embedded neutron detectors, and then finally the work I'm going to talk about is just this class of electrically conductive polymer composites. And so the reason that we are interested in this research is that we're very motivated by this static charging issue that is intrinsic to any material that's not electrically conducting, which includes pretty much all polymers that have ever flown into space. It also has, and as an example, I won't cover these in detail in this talk for brevity, but I would draw your attention to the Eureka STS-57, where you can see this photovoltaic cell that is shorted out electrostatically and led to real mission problems. There are also concerns related to lunar dust. I'm very fortunate to have been placed in this order after somebody who went into so much detail about this. But as you might imagine, having an electrically conductive surface can present some design strategies in dealing with this issue. And then finally, we care about polymers in general because they're generally good at radiation shielding, especially for their weight. So if we can overcome some of these risk factors, such as not being conductive, then it makes them more useful in general. And the way we do this is use a type of modified reduced graphene oxide. And reduced graphene oxide is kind of a graphene analog. It's not as conductive as pristine graphene. It has defects, but it's much more scalable. And so what we can do is take this reduced graphene oxide, we chemically functionalize it. This process is covered in detail in these two publications and cited here below. But as you can see, we can create these dispersions in a variety of solvents, and we can use these dispersions to coat plastic materials, which we then perform various post-processing procedures on. And that leaves us with a substrate that looks like this up here in the top right. And this is actually an older sample. I'm showing you a rougher one. It's one of the better, easier images to see good parts and bad parts. And if we look at these bad parts, we can see that it's quite rough. And in this SEM here, you can see that while the sheet resistance of this material is less than 20 ohms per square in general, there are these void structures. And when we think about, that has implications when we think about lunar dust and space applications. So the key features of these films are that we've got a scalable and very electrically conductive solution to the problem, but we have this roughness issue. And that's what I'm going to talk about in these next few slides. So when we think about these samples, there's a lot of ways you can see the roughness problem. And so in these samples that I'm showing you here only vary in the amount of coverage that was applied to the substrate. And then also, I just want to point out that all of these are on a PEEK substrate. So PEEK is a polyether ether ketone. It's an aerospace grade plastic. So you probably don't have any of this in your home, but if you think about a material that you might want to manufacture a plane part out of, or certainly parts of a spacecraft, PEEK would be a material that you might consider. In the far left, we have optical images. The middle column here is scanning electron micrographs, and then on the far right, we have profilometry. And in all three, it's pretty easy to see that there's a big link, or there's a big change in roughness with the amount of material that we have here. And then also it's variable. So if you look at this middle column here, it's very inconsistent when we start adding a lot of graphene. And that's due to the issues with the melt processing procedure that I'm not going to cover in great detail here. And then we'll come back to these profilometry images. So just kind of keep that in mind. So to the lunar dust issue, and this is, again, I'm very grateful in the order in which we've presented here. The voids on this surface are a very big potential problem, we think, into using this type of a coating on a material in space. If you look in this figure A here, this is the size distribution of lunar dust collected during the Apollo missions. And there's a region here that's sub, 1 micron. So this is in the nanometer scale range. So basically these dust particles, there's a vast population of dust grains here that could penetrate these voids, and they get in there and they break up the surface. And so on the one hand, we have an electrically conductive surface. So we can get rid of the statically charged particles that we would expect to see in operations on the lunar surface. However, there's this size exclusion issue that we haven't really tackled yet. And so to kind of explore this ourselves further, I've done some research with a colleague, Micah Scable, who's also part of the REVEALS program. His research looks at various aspects of simulant dust performance, and mainly in more bio-focused molecules. However, he is helping me out in looking at my coatings as well. And so here we have an apparatus where my sample can sit in a tray and it gets charged dust grains dropped onto the surface. We can charge these things through tribocharging, so just vibrating the surface, or we can use an electron source, depending on the experiments that we're running. Very quickly, if we look at these samples, here are the profilometry scans that I showed you previously, 2 of the samples. And if we expose those samples to charged simulant dust, we can quickly see that there's a big difference between the amount of dust that's on the surface and then the roughness, and the starting roughness of the laminate layer. Not only is this readily apparent in the profilometry scans, and I apologize for the difference in units here between nanometers and microns, but the red and blue are still orders of magnitude high and low, so the pictures are still somewhat descriptive. But we can also see it just optically. When we take a picture of these are relatively small samples, but when we look at the intensity of the grayish white color here, that's the dust that's stuck to the surface, even after it's been removed from the vacuum chamber. The gray is much more intense in the rough surface rather than the smooth. And we also see a pretty big change in the sheet resistance of these materials, although I will note that both of these are still fairly conductive and would be able to serve any other purpose that we might design them for. And so a lot of work has gone into this. This will be a focus of a later publication, but given the 8-minute talk, I just wanted to draw your attention to it in case it piques your interest. We are considering different processing options such as spray coating. And then we've taken a closer look at some of our melt processing, some of our melt processing steps to form these nice uniform coatings. And so this is more this is more representative of what you might see laying around our lab and that's being used in our proposals these days. So much smoother, much more uniform, and with similar sheet resistances. And this is a picture of polyethylene just to show you something different than PEEK. So this can be applied to a variety of thermoplastic materials, which is why we like it. And so just as an example of a different application that you might consider these things for, we want to think about different applications. And they actually serve pretty well as joule heaters. And so we can think about this as de-icing, or you could even imagine the same principle, melting a frozen volatile in ISRU type applications. You can use these conductive joule heaters as a means of setting up thermosetting materials, which could also be incidentally used in like repair schemes on the lunar operations or in space. You have a viscous thermoset epoxy, apply current to the material, heat it, and it would fuse any damaged areas. And then finally, you can use this as an indicator that damage is occurring in the surface. And there's a big field that's really popping right now with examples of various groups looking at joule heating performance as a function of material strain or an inherent damage to the surface from a variety of sources. And so again, to quickly frame this in this work, this work is ongoing. We have been able to reach 100 degrees Celsius at only 20 volts. This is on an older sample, this image here. But this is really nice because this is a fairly large substrate, so 7.5 by 15 centimeters. And we're able to boil water off of it, which is nice and provides a lot of opportunities in a variety of space exploration use cases. And so just to briefly summarize, we started off this venture with thinking about static charging, and we've ended up beating the performance we needed to do this by at least 10 to the 6 ohms per square. And then we're looking at lunar dust mitigation concepts. So right now, these are early stages, but we hope to transition to schemes using more advanced systems like an EDS system that you would conventionally see from NASA. We've talked about joule heaters, and then of course, like I briefly mentioned at the beginning of the talk, the graphene is also being looked at in EMI shielding and real-time dosimetry cases. And then we could also envision these types of things in structural monitoring. So you really have a one layer kind of does a multitude of operations, or at least has the potential to. With that, I would like to thank the SSERVI Institute and NASA REVEALS that's funded this work and helped facilitate it. The John Reynolds Research Group, where I've done most of the synthesis, and the material handling, and then a variety of people that have helped to make this project possible in one way or another, listed here at the bottom. So with that, I'll take the remainder of my time to take any questions, if there is any.
Thank you very much. Very interesting talk. We're over time, so we're going to move to the next speaker, and I'll hand it off to my co-chair.
The next speaker is John Rask. He's going to be presenting the topic that is entitled Chemical Reactivity on In Situ Lunar Dust for Biotoxicity Assessment. So John, thank you.
Thank you very much. Are you able to see my slides?
Yes.
Okay, I'll run the timer behind me.
Okay.
This activity is a collection of a lot of work by many different people. Penny and I put together some of this, but there's folks from Ames, JSC, the National Institute for Occupational Safety Health are involved. So there's many, many more people that are involved in this. And I'd like to say thank to everybody for that. So today I want to give you a flavor for, I always heard about lunar dust in the context of the lunar environment and how its reactivity is important as it relates to biology. And so I will go through a handful of examples here to demonstrate that. And of course, just as a quick primer, most of what's in lunar dust is silica glass, but the material that I'm particularly interested in this talk today is the metallic iron or the nanophase iron that is relevant to chemical reactivity. And as we've heard throughout the day, the lunar environment is continuously bombarded by full spectrum UV, solar wind protons, galactic cosmic ray, solar proton events, and impact processes. And all of these things impart chemical reactivities upon the mineral grains at the surface, including the process of grinding it down into smaller and smaller particle sizes. And we have learned from other studies that transient increases in chemical reactivity and physical processes of mineral specimens have been shown to affect human pulmonary toxicity. This is in particularly in reference to silica. So we've done a lot of studies with silica, and in the studies that I'm going to be talking about in the future, we actually worked with Apollo 14 specimens. So what do we mean by chemical reactivity? Simply put, it refers to radicals that exist on mineral grains that can interact with oxygen and water. And these are referred to as reactive oxygen species, including hydroxyl radical, superoxide, and peroxide. And we'll hear more about that later in Donald Hendrick's talk. And biological exposure to mineral grains and its chemical reactivity will elicit an inflammatory response that leads to the production of reactive oxygen species in the cell itself. And so we have explored ways to bake material or expose it to water and oxygen to decrease its chemical reactivity. And of course, the other phenomenon in the lunar environment enhances it, as mentioned before. So are there ways that we can study this with samples we have? Yes, we have samples from the Apollo missions, and of course, there's samples from Russian missions. And of course, not pictured here is the samples that have been brought by the China mission. And we have learned over the last 30, 40 years that lunar dust is definitely chemically reactive, and Apollo specimens have been used for a variety of studies, looking at infectivity and toxicity studies. And some of the earliest ones looked at dissolution changes and UV optical properties that were altered upon analysis. But the most recent and more dynamic results in terms of crushing lunar dust was done by Billy Wallace and others. They discovered that it's much more reactive in its freshly crushed state, similar to silica. And one of the most profound visual references, in my opinion, is the fact that we have learned that hematite has been observed on the moon. And we also know that hematite nanoparticles are toxic to bacteria. So just to further emphasize this, in the north and south pole regions of the moon, the colored yellow to red areas are enriched in hematite. And so this is another clue that there is a reaction going on, or in the past, that is combined iron oxides and nanophase irons are reacting with oxygen and water to form hematite. So we know that there's chemical reactivity going on in the moon's environment. And much of that is attributed, as we've heard throughout the day today, about nanophase iron, and that is something that's appearing in the rims of each of these little tiny mineral grains. And up in the upper right corner, to emphasize the fact that there is elemental iron in there, Larry Taylor used to always carry a magnet around to demonstrate how each individual particle of lunar dust is attracted to a magnet, demonstrating the fact that there's elemental iron present. And another thing that came out of Wallace's study and a lot of work that Larry Taylor and others did was the point of reactivity relates to the mineral maturity, that is how much elemental iron is present in the samples. And hydroxyl radical scavenging assays have shown that mature samples are much more reactive than immature samples. And it's important to note that lunar soils at the surface become more mature over time due to space weathering. And we know that the lunar surface is very different all over the moon. And so the site of location where you're working is important in terms of analyzing that actual sample. So there's been a lot of work done on reactivity analysis of lunar samples and simulants. And the main takeaway here is that I want to emphasize that both NASA and Russia have independently observed that Mare samples contain more nanophase iron than Highland samples. And as we mentioned before, Mare samples appear to be more reactive than Highland samples. And also, there's been a number of biotoxicity studies that have been performed both by the US and Russia. And Mare samples have been reported to be more biotoxic than Highland samples, although the Russian studies were a little bit flawed because some of their particle size controls were less effective than the LADTAG studies, which were highly particle size controlled. And so our take-home message here is that lunar dust chemical reactivity is predicted to be enhanced in the lunar environment. And to drive this home, we've done some biological studies in rats. Biological response is going to increase as a function of dose, and the dark line on the right is considered a passivated or low reactivity sample. And if we chemically activate lunar material, it will shift the biological dose response curve to the left in what we would call a chemically activated dose response curve. And this is in fact what we observed in a series of animal studies in rats, where we injected small doses of lunar material from the Apollo 14 field site into animals. And we used 3 different preparations of lunar material: ball milled, unground, and jet milled, 3 different preparations of the same material. It was particle size controlled. Roughly about 2.5 microns or so was injected into the lungs of these rats. And we measured the inflammatory response of the cells that responded to this injection of dust in the lungs of the rats. And the short story is that that material, which was more highly chemically reactive as assayed by the hydroxyl radical scavenging assays we've used, was more biologically toxic. Although the difference was small, it was highly statistically significant in terms of it being more impactful in the lungs of the rats. So this is a very important observation that we had made here, and it further emphasizes the importance of chemical reactivity as it relates to its biological effects, in this case, in the lungs of rats. But more broadly speaking, chemical reactivity is critical, as we've heard also in this session, to human health, but also space biology and astrobiology. And it's important to remember that radicals contribute to cell death. They contribute to signal transduction disruption, gene expression changes, and oxidative damage to nucleic acids, proteins, and lipids. And this is important in the whole scope of all biology. And we also want to point out that radicals rapidly react with organic molecules, and they interfere with assays and other methods. And in some cases, they can damage instrumentation. And it's important also for us to be considering that Earth-based analogs, simulants, and archived lunar dust do not fully represent the picture of in situ reactivity and biological effects. What we really need to do is take a measurement on the lunar surface and compare that to what we can measure here on Earth. And even more broadly speaking, in terms of engineering and hardware development, future engineering tests that use hardware destined for the moon that is sensitive or is going to be involved in some aspect of chemistry of the lunar materials, those tests of that hardware must be conducted on appropriately treated specimens, that is, those that most appropriately represent material from the in situ lunar environment. And with that, I'll stop and thank everybody for your attention.
Thank you, John. Interesting topic and talk. I would have a question and I will post on the chat, but if anyone has also a question, please include on the chat and we can also discuss that later on the discussion. Thank you. So moving to the next talk, we have Donald Hendricks, and he's going to talk about hydroxyl radical generation of lunar dust analogs in biologically relevant human respiratory system fluids.
Give me a second. Thanks, Douglas.
Yes.
Hold on, give me a second. Okay, perfect. Okay, thanks. Okay, so the point of my work is to understand the health effects of lunar dust. And so how I do that is I assess the reactivity or the OH radical generation of different minerals and lunar simulants and try to understand the potential inhalation health risks. So as John said, reactivity can mean many different things. It can mean generation of peroxide, generation of superoxide. I'm primarily focused on OH radical generation. And the reason I focus on that is because OH radical has been known to be cancerous to lung tissues.
Hey, Donald, real quick, this is Mike. We're seeing your presenter view at the moment. If you want to either swap displays or hit the mirror mode.
So actually, let me, oh boy. Let me do, let's see. Does that work?
Yes, thank you so much.
Oh, awesome. Yeah, thanks. Okay, so I'm part of the RISE 2.0 team, and within that team, I'm part of the Theme 3 group. And so what the Theme 3 group does is we try to understand the health effects of lunar dust through a variety of methods. First, we're trying to develop the next generation of lunar simulants, and by that, trying to make current lunar simulants more lunar-like, like by adding metallic iron, which I'll talk about in a bit later. And so what we also do is we assess the reactivity of these simulants, which is what I'm going to talk about today. And the next talk, Jamie's going to talk about evaluating the toxicity of these lunar simulants. And so far what we've done is we've obtained 3 separate lunar simulants, the traditional JSC1A. We've obtained LHS1 from the Exolith lab, as well as LMS1 from the Exolith lab. And since these simulants by themselves do not have metallic iron, we try to add some metallic iron. So basically how I do that is I take like a little silica boat and I add a little bit of the simulant sample, and that silica boat goes into the glass tube. And this glass tube gets flushed with hydrogen. Can you guys see my mouse?
Yes.
Awesome, yeah, okay. Okay, so yeah, so this tube gets flushed with hydrogen gas, and then this tube gets placed into the furnace. And that's heated to 900 C for 15 minutes. And then we remove our samples once they're cooled down. And we notice that they are visibly darker. And under SCM, we see all these little blebs on the surfaces of the grains, and these grains are metallic iron. There was a paper by Allen et al. 1994, which they used a similar method that we used, and they were able to determine through SCM and Mossbauer spectroscopy that these little blebs on the surfaces of these grains are metallic iron. And this is an SCM image of JSC1A grains. And in addition to that, what we've done is we've assessed the reactivity or the OH radical generation in 3 separate fluids. We did first in DI water, then we did it in simulated lung fluid, and then in artificial lysosomal fluid. And so simulated lung fluid simulates like the fluids in your air passageways, and artificial lysosomal fluid replicates the fluids in your macrophages. So I have here an SCM image of some macrophages. And so we're trying to simulate sort of what's inside of those and how reactivity would be affected once those macrophages engulf any inhaled particulate matter in the human lungs. So here's just the list of what's in both the simulated lung fluid and artificial lysosomal fluid in grams per liter. I highlighted in green the amino acids, and in red, DPPC is a surfactant that is commonly found in lung fluid. And so how we measure OH radical is through a technique called electron paramagnetic resonance, or EPR spectroscopy. And so basically what we do is we take about 100 meters squared per liter of sample, that's based on the surface area of the dust simulants. And then we incubate that in half a milliliter of an organic compound known as DMPO. So this is the organic molecule, a DMPO, and that will react with any hydroxyl radical generated in solution by any of the three simulants. And that will form this stable organic radical compound, which can then be measured very easily using the EPR. Because we can't measure OH radical directly, because OH radical is very reactive, so we have to sort of trap it. And that's what the DMPO does. So here are the results of reactivity in DI water. So R denotes the heat treated and reduced samples, and we highlighted the results of the reduced samples in red. And so as you can see, heat treatment and reduction of these samples leads to a large increase in the OH radical generation compared to the not reduced samples in the gray. And so this is very likely due to the presence of metallic iron, and kind of shows how drastic of an effect the presence of metallic iron alone can have. And there was the other paper that John also talked about, Wallace et al. 2010, where they tested the reactivity of various Apollo samples and compared that to fine-grained JSC1A, and they were able to see that there was a huge increase in the reactivity compared to the fine-grained JSC1A. And they were also able to strongly correlate the reactivity with the maturity, or pretty much the amount of metallic iron that was present. So the advantage of this is that we can make these samples in the lab versus having to actually get pristine lunar regolith. And so this is where it gets kind of interesting. This is not an incomplete graph. So this actually shows the results in ALF and SLF, and we actually were not able to get a measurable signal in either of these fluids. But that doesn't necessarily mean that we're not making OH radical. It could also be that we're not making OH radical, but in the next slide, I'm gonna go over some bullet points on what may possibly be happening. And so first, we saw in DI water that heat treatment and reduction leads to a sharp increase in the reactivity, and that's very likely due to the presence of metallic iron. So there was no measurable signal in the simulated lung fluid or the artificial lysosomal fluid. So the first point I have here is that it may be possible that iron on the surface of these grains are being chelated, or sort of being bound to any of the electrolytes present in both of these simulant fluids. And so if that iron is being bound, it's not able to participate in any type of chemistry that leads to the generation of OH radical. In the opposite case, what could be happening, the amino acids in both of these biological fluids, especially in the SLF, since SLF has more amino acids, is reacting with the OH radical at a rate much faster than that DMPO molecule can trap the OH radical for measurement. So if that's happening, there's no way that we can measure it using EPR. And on top of that, the sort of the negative health implication of the OH radical reacting with the amino acid is that since your proteins are made up of amino acids, if you inhale any lunar dust that immediately starts generating massive amounts of OH radical, that's going to interact with all the amino acids that make up your proteins. So then your proteins may start to sort of unfold and denature and lead to a whole bunch of other, bad stuff. And as for the artificial lysosomal fluid, it includes compounds like sodium tartrate, very high levels of sodium hydroxide and citric acid. And so it's possible that some of these reactive sites on the surfaces of these dust grains may sort of, in essence, be washed away or dissolved before it has a chance to make OH radical. And so to conclude, heat treatment and reduction leads to massive increases of OH radical in DI water, at least, and that's very likely due to the presence of metallic iron. So we were not able to measure OH radical in simulated lung fluid or artificial lysosomal fluid. However, that does not mean that we're not making OH radical. It could be that we're not, but in all honesty, it could be, you know, a mix of both. It could be there's some components in the biofluids that are preventing OH radical from being made, and there's other components like the amino acids in the biofluids that are very rapidly reacting with the OH radical. And therefore, we're not able to measure it because the DMPO reaction with the OH radical is much slower than that of the OH radical and the amino acid. And currently, we are awaiting Moss-Bauer data for reduced simulants, and that will give us a much better idea of how much metallic iron we have in our samples compared to actual lunar samples. And with that, I'll take any questions. Thank you.
Thank you, Donald.
Oh, wait, should I reshare? Sorry, I kind
of. Does anybody have any question for Donald? I would have a quick question. In terms of comparing maybe the effects of in situ lunar regolith or on those biofluids, do you have an idea, or how could you perform experiments on those not losing the toxicity or chemical activity of the dust specimen?
Like you're talking about, you said in situ, like on the actual lunar surface?
Yes. Would there be any plans to do that?
There's not any plans that I'm personally aware of, but that would honestly be the best option because, you know, it's really difficult to replicate actual lunar dust. And I think there was a whole session sort of on that. And so, you know, having, you know, an instrument up on the surface would actually be superior because we could sort of get, you know, what, you know, what effect, you know, do these actual lunar dust samples have, you know, on the human body. I think there was an instrument called Luna Chem, and I think John, actually, you were looking at that, right?
Yeah, we were working on developing an in situ measurement device.
Yeah, no, I mean, in situ measurements would be ideal because also a lot of these Apollo samples that are being used, you know, were not necessarily stored in the best environments. So that's something also that has to be kept in mind as well. And it's very difficult to replicate agglutinates and other things. So yeah, that would be very ideal.
All right, yeah, thank you. We can also keep the discussion after, but let's go to the last talk with Jamie. And
okay.
The talk is about damage provoked by exposure of human lung
recording
cells
stopped
to lunar regolith simulants.
Okay, let me just share my screen. Oh, can you see anything?
Yes.
Did you stop the recording on purpose?
No.
Oh, hold on 1 second, please.
Recording in progress.
Okay, thank you.
I'm actually start. Hi everyone, this is Jamie. I'm a pharmacology PhD student at Stony Brook University, and today I would like to talk about my project, also collaborating with Donald, about the damage provoked by the exposure of the lunar regolith simulant to human lung cells. So first of all, as John has already mentioned, so lunar dust can be really tricky to deal with based on like a lot of previous report. I'm not going to repeat that here because of the time. And although it's somewhat similar to what it's made of with the terrestrial dust, but it can be more toxic and reactive. So, and as John has also said, it's exposed to space radiation, solar wind, and other stuff. So, so that's why it becomes so reactive. And There are a lot of like astronauts in the past talking about this also. So that's why we would like to look into this kind of issue. So based on our previous research, based on the paper we have published in 2018, we hypothesized that after occupational exposure to lunar dust simulant, lunar dust, those lunar dust will lead to DNA mutations, no matter in nucleus in the cells or mitochondria in the cells, which this organelle is responsible for the energy production to maintain the survival of the cells. But the nuclear DNA and the mitochondrial is kind of somewhat related to each other, so they cannot live without each other. Once mitochondrial has some dysfunctioning happening there, it will also lead to some problems with the nuclear DNA. So with this kind of phenomenon happening, it'll lead to further tissue damage and elevated cancer risks, such as lung cancer or other part of the tissue that may be exposed to lunar dust. So as Donald has also said, we will basically, we got the samples from the NESFELS lab, and we will do a size exclusion and grind it up to around 10 micrometer. And for some of the samples, we'll treat it with hydrogen gas at 900 degrees Celsius to simulate the solar wind on moon. So we'll just call it for reduced material, and we'll also like compare the differences later and when I talk about my experiment. And basically for all of the time, we'll store it in vacuum desiccator, and before the experiment, we'll grind it up again to make sure that the side is not oxidized, and then we'll directly apply to the human lung cells. So here's the breakdown for the two lunar dust tubes. It's what Donald just mentioned as well. So first of all, I would like to give everyone an overview. So basically, after the lunar dust was like applied to the cells, we can see a significant differences here. Like the cell viability was like strongly decreased, with the dose dependency, as John also mentioned, I believe. But for the reduced materials, when cells are confronting them, it can be like worse. Like compared to the untreated one, it can be worse. And it's also happening, there's also dose dependency for the reduced samples, although they're quite low here. Let me see. Okay. And next, after looking at like a big picture of what's happening there, we would like to see if the mitochondria is like facing any issues. Are the function impaired? That will affect something else. So we would like to give everybody an overview with some images. So with the untreated control, there's nothing added. You can basically see nothing in the mitosox rat dye, which is a probe that is good for detecting the superoxide inside the mitochondria. So you can see here, after treated with some positive control, there's some like round stuff forming here, which is the mitochondrial complexes being stained. So you can see that's happening. And we can also see some of them after they're treated with some of our lunar dust simulants. And when the cells are under really high damages, you can see some of the cells are deformed and they're just not looking good. The nucleus are also stained. That means like the cells are under severe damage. It's really bad. And then we quantify it with the plate reader, and we also found a dose dependency, which is not listed here because of the time limit. And we also found out that the reduced samples are also showing like much higher superoxide levels inside the mitochondria. Okay. And next, we would like to see if the mitochondrial DNA is also affected, because that's also responsible for encoding some of the proteins that's important for the mitochondrial function. So we use a PCR assay to do so. And we have done 2 PCR, which will probe the shorter fragment and the longer fragment, and we will use the ratio to normalize our results. So when we see like a lower ratio, which means there's more DNA damage there. And our results also show the same thing, that after the exposure to the reduced samples, you can see a much more like dramatic, much more apparent decrease in the level in the DNA damage here. So basically, it's showing the similar stuff, like the cells are under serious damage. The mitochondrial function is like extremely impaired. And we also like to see that for what we haven't seen before, we haven't published it, is that if the nuclear DNA is also under serious damage. So we use an assay called alkaline combat assay, which allows us to lyse the cells and then run an electrophoresis and check on if the cells are if the nuclear DNA is under damage. And you can see here in the control, they're looking pretty intact, and you can see the round shape here. But when we expose it to different simulants, you can see like there are tails forming, which indicates that it's under like serious damage. So I think I have to wrap up. So for all the results I have shown, both simulants, including LMS1 and LHS1, they both cause dose-dependent cytotoxicity, mitochondrial function, which is the superoxide level, and the genotoxicity, which includes the assay I just told you, and also the assay we use to detect the mitochondrial DNA levels. And the reduction of both materials leading to enhanced toxicity. So you can basically see that apparent effect easily with all these assays. And we are also interested in detecting what some other minerals that's composed of the lunar dust simulant we're currently using, and we would like to see like what kind of minerals may be the main toxic components to cells. And lastly, although like we see a lot of damaging effect here, but we're not sure like physically or chemically what exactly things are happening, because in our previous published literature, we didn't really see the correlation that Donald has found, like with some reactivity effect, it just didn't match with the cell response. So we guess there's something still happening there. We haven't found it. And we also are working on doing in vivo experiment, as John has said, with the rats, with our collaborator. I hope he's here, Greg. I'm not sure if he's here, and to validate if our in vitro result is like really real. So that's all for my presentations. Thanks a lot for listening. I'm happy to take any questions.
Excellent. Thank you, Jamie. So if anybody has questions, please, you can also just raise your hand or unmute yourself and speak verbally, because we are going through the discussion session also. Or also include the questions on the chat.
Yeah, I guess I don't mind, yeah.
So yeah, go ahead.
Sorry, this is Elizabeth. I realized I forgot to raise my hand. Yeah, and I'm getting some answers to my question in the chat as well. But I guess my general question, like for this session, was like, is there any way to, like, you know, relate like the toxicity that you're seeing with how someone's immune system might respond? Just because it seems like there's a lot of variability in people's immune response to things. Like I have issues with my own immune system, so like I probably read more about this than I should, but like also I'm thinking of like even with like COVID-19, it's like, you know, some of the damage is from like the actual damage to the cells, but then it's like, you know, what the immune system does with that can like make or break the situation. So I'm just curious about how you might account for that.
So basically, I will say probably this one will be a better move, because like there are a lot of like immunity is a lot like related to the kind of the superoxide. I think John has also mentioned that, like the superoxide levels and the ROS inside the cells. So when like there's the stuff, for example, the lunar dust stimulant, when astronaut breathe them in, and it'll lead to like a lot of generation of the ROS that the cells cannot really deal with it, then this will lead to some immune response, I believe so. But I'm not an immune person, so, but like from what I learned, that's all I can tell you. Yeah, that's a good question though.
Yeah,
we may need to look into more like cytokines and stuff to like confirm like how highly it's related to the immunity. But yeah, that's a good point. Yeah.
Yeah, I'm seeing here that Ron has the hands up, so you can ask your question. Feel free.
Yeah, go ahead.
Can you hear me, Ron?
Yeah. Oh no, sorry.
Ron Creel, if you're available, feel free to answer. And for everybody, we've entered into our discussion period. So feel free to chime in, everyone.
Well, can you hear me now?
Yes, sir.
I've been trying to preach this for a long time to folks for many years. We cannot hardly simulate here on Earth what's going to happen on the moon. But over and above that, gosh, guys, we've got to get in front of NASA people and share this information you've told today, because it's a real hazard to the astronauts to go back up there and spend any extended length of time and get exposed to the dust. We need to have suit covers. We need or leave the suits outside. We need to have airlocks, which would help us. We need to get serious about this, and I'm not getting good response from NASA folks up to date.
It's a point well taken, Ron. The dust problem, as you know, was something that the Apollo missions were aware of, but they didn't do anything to mitigate it. They just tolerated it. But because those missions were of very short duration, the total dose exposure was limited. And so now there's a fair number of efforts going into, as we've heard in this series of talks, technologies that are designed to remove dust from surfaces, to potentially passivate airborne dusts through a variety of different techniques inside a habitat, and or through using a variety of different engineering controls. But you're correct in that they're clearly, this problem is not going away. And this is not just something that we're going to be experiencing on the moon. If humans go to Mars, we will be experiencing it there, and on asteroids as well. So the dust problem is sort of ubiquitous wherever humans are going to be exploring. And I agree with you that there needs to be a concerted effort in looking at the in situ nature of these materials because of the exotic nature of the lunar environment, and seeing how that compares to what samples we have here on Earth. And what we might learn is that there's a big difference, and that the permissible exposure limits might need to be revised. On the other hand, we might learn that our permissible exposure limits that were developed from Apollo 14 specimens is pretty close to what we expect in various different locations. But I would wager to bet that there's going to be natural variability from site to site on the moon, as we have heard throughout the conference, of how varied the surface is, and the chemistry of the material there is going to have a large impact on technology and biology.
I can't fully agree with you. I mean, we've got to keep the dust away from the astronauts' lungs. The way you do that is you keep the dust outside. I keep bounding on people. You can't bring the dust inside the habitat. They commented on Apollo 16, Charlie Duke shared that they got back inside, they kept their suits on because the dust was getting so bad that when they docked with the command module, the poor fellow automatically had to bring a vacuum in there and try to get rid of it, but it still exposed their lungs to the dust. And it was a short duration EVAs, maybe 20 hours outside the exposed. We've got to get everybody really attuned to this. This is a major issue.
I would agree. It's not going away. Doug or anybody else in the panel, do you have anything to add or contribute to Ron's points?
Yeah, I would be interested to know if any of those new studies would change the threshold that we currently have for the exposure, consider safe exposure. Yeah.
I don't think there's any such thing as safe exposure to lunar dust.
Safety.
There's no safe exposure. You've shown that in these presentations up today.
It clearly has a biological effect. And in my opinion, limiting that exposure to as little as possible, and if we can completely eliminate it, that's the best scenario. I would totally agree.
Okay.
Yeah. I know there are systems for like monitoring people's radiation risks over time, like in space environments and otherwise. Maybe there's, there has to be a similar metric where it's like, yeah, obviously nobody wants to get irradiated at all, but like when do we start like ringing all the alarm bells after like a certain amount of dust exposure? Like that'd probably be really useful.
Donald, I mentioned, sorry, go ahead.
On the Apollo landings, we got very lucky. There were no solar flares during the time that the Apollo missions occurred. If there'd been a solar flare, we might have gotten severe exposure of a whole lot of bad things on the moon. Not to mention the micrometeorites. I saw some presentations yesterday that showed high densities of micrometeorite exposure. But let's get back to the lunar dust. Keep it out of the astronauts' lungs.
Yeah, this is Tom Orlando. We have a program in that in our Reveals Survey Center. One thing I want to point out is, in addition to these important studies that were just discussed, a significant fraction of the dust which isn't studied is in the nanometer size regime. The nanometer size particles are the ones that are taken up rather immediately, and they're not monitored, and those are known to have massive toxic effects here on Earth even. So I think it's a bigger problem than these talks demonstrate, because the toxicity of the nanometer particles are really high.
Yeah, I would agree with that. Anywhere between 5 to 20% of the lunar surface, or 15 or so, of that material is respirable in nature. And as you accurately point out, there clearly are increasing toxicity effects as the particle size gets smaller. There was somebody about to jump in there. I'm sorry.
I was going to make a quick comment.
Yeah, please, Donald. Yes.
Yeah, that anything below like 1 micron can very, very easily just be absorbed by the circulatory and nervous systems. And, that can settle even into the brain. And I think there was a study, it wasn't lunar related, but they found that high levels of magnetite in the brain through air pollution led to Alzheimer's, or led to a higher chance of Alzheimer's. So, if people are up on the moon, for months and months, I think they're going for 6 months or something with Artemis, if I'm not mistaken. And I think the next Artemis mission later in the decade is supposed to be longer than that. So, you want to try and protect these people from, not succumbing to these sort of long-term diseases, like potentially, I don't think there's any magnetite on the moon. But if you're having, lunar dust grains settling into your brain, that could lead to many other diseases, neurological diseases, later on in life. So that's something that needs to be looked at. And I don't think many people have really tried to find ways to mitigate, the smallest particles. Everyone, is looking at particles less than 25 microns, less than 10 microns. But what about less than 1 micron, less than half a micron? That's still pretty prevalent on the moon.
That was what I was had a question about. I didn't realize that the nanometer particles, I just missed that it wasn't being accounted for, I guess. Are there even masks or filters that can filter nanometer size particles?
I thought filters can, I think, down to 300 nanometers, but I think there's studies that have been done that there's dust particles smaller than that, down to like 100 or even 50.
Yeah, that's for sure. And actually, this is a huge issue right now for indoor air quality for COVID transmission.
Right.
Yep.
I think the best thing. Oh, sorry. Go ahead.
I hope you could take that. These session organizers can take a summary here forward to somebody to come out of this conference with some kind of positive way of getting people attuned to the fact that you've got to get the lungs, keep the lungs clear of this, and the lungs is just going to transmit it into the brain, into the bloodstream.
Mm-hmm.
So let me point out something. So there is a pretty big effort here on Earth to deal with getting rid of these sub 300 nanometer size particles for the indoor air quality issues associated with COVID. These technologies can easily and should be adapted to habitats in space.
NASA did extensive work on suit covers at ILC Dover, and as well as significant studies on airlocks at NASA Ames. And I see some hope that Elon Musk's vehicle quotes a couple airlocks. So we'll see.
There's definitely suit lock technologies and these kinds of things that are in development. And I like that operational approach to keep the dust out.
So I have a question on that. I mean, so you're going to need to have some kind of a diagnostic probe to determine whether or not you kept the sub 300 nanometer particles out. Yeah. You know, you can't use the scattering technique very well with this size particles. So is there some technology that's being developed to show how good the airlocks are?
Yeah, how are we going to be able to sample the air or surfaces in future missions of what dust may be present that we can't see? I don't have an answer for that. Does anybody else?
Yeah, I don't think that's really possible. I mean, probably I don't know it, but like, because I also have read some papers about air pollution, and it's also like remain a hard issue to like deal with those nanoparticles inside our air. Like when you're living near factory or stuff, it's just the way it is, unfortunately.
Hmm. You could take one of those COVID filters and, you know, suck air through it for 5 minutes and then see how dirty it got. I'm not an engineer, by the way. But yeah, I was kind of thinking that too, Tom, about how we've just had all of this research happen very rapidly about like COVID and transmission of really tiny particles that are very difficult to manage through the air. So,
I mean, the best way. So we're developing technologies for this for indoor air venues, and one of the better ways of doing it is related to one of the talks where you have field emission of slow electrons and you electrostatically precipitate these out. And you collect them electrically, right? And you basically have an electrostatic cleaner. You got to have good throughput in the indoor air, but there's ways of designing that for that to work.
Yeah, and another interesting point too is that obviously nobody's going to be exposed to material that's out on the lunar surface. It's only going to be inside spacesuits or in a habitat. And if that respirable size material gets into the atmosphere, it can stay lofted in a reduced gravity environment in that atmosphere in a habitat for extended periods. So this is another topic to be considering as we're developing, future follow-on missions and habitats and so on.
I might jump in just for a second. I've worked with some particulate matter analysis people and in measuring dust particles in atmosphere that can go down to 10 nanometer size. It's not a scattering technique, but it can measure particles down that size and get particle size distributions. But they do have scattering techniques that get to about 100 nanometers in size. So it is possible to measure these size ranges.
What kind of, Jeff, what kind of device was that or technique? I'm familiar with sort of a benchtop microtrack or blue wave microtrack that can measure particle size using me scattering, whether in air or in a liquid vehicle.
So one is I believe it's called a GRIM instrument as the company, and it uses laser scattering on single particles in a flow. So you could use that in a habitat. Then there's also electrostatic classifiers, and you can parse out grain size by their size, electric charge interactions. And for the really small grain size, what you do is you actually end up growing it in a solution, and you know how much it's grown, and then you can go back to its original size. So you can do it that way too. I forget what that's called.
I'm wondering if any of the other panelists have other thoughts on this topic. Like, for example, Ben was developing technologies to remove material from surfaces, maybe through his lenses, or the other participants have some more ideas. Is there anyone, any of the other speakers that might want to chime in?
Well, yeah, so we've been developing these technologies for COVID, and we also have a project for NASA, and they're basically going in parallel. There's actually an electrostatic glove that the students at Georgia Tech are putting together, where you can electrostatically brush off stuff, and it would be a tool that the astronauts use to brush themselves off before they get into the antechamber. But all of these are basically due to nucleation and growth and charging of the grains, and sort of utilizing the sort of the electrostatics to get rid of them. So they're just sort of removed but not destroyed.
I challenge folks that all of this is wasted housekeeping time. It's wasted science time in housekeeping.
Sure, I agree.
By the way, we did an awful lot of that on the moon. When it all was over with the rovers, got them, the final rover back there, we sat there and we said, my gosh, we have made the astronauts try to brush off the dust, which didn't work, even though it had been shown before the missions that it would work here on Earth. Didn't work on the moon. And they were very frustrated. I can send you all the 2-minute video that was made using the TV camera of Charlie Duke and John Young trying to clean it off their suits. Whether a electrostatic wand would have helped, who knows? It's just awfully dirty up there. Also, I want to point out to y'all, the dust does not stay on the moon. The dust can be propelled up into orbit around the moon. There are studies that there's considerable dust can be up there in the gateway, getting toward the gateway. Hopefully we won't ingest it there.
So I have a question which is related to your comment about dusting off. So we philosophically don't buy into that either. Zach Siebers gave a talk, and the reason for making these conductive polymers is to put a laminate on the suit where you can electrostatically repel the dust, and therefore you're sort of actively removing them. So I guess I would like to hear from some other folks whether or not they think that's a good idea and a viable pathway.
I mean, that's pretty similar to the research that I've been doing, using the conductive nature of the dust just to try and, electrically repel it from whatever surface you're concerned about. So I mean, like what you said about the electrostatic glove and, covering your suit or whatever in the electrostatic material, that's all stuff that I've heard about, and it seems like very, very good method to keep the dust off the astronauts and out of the actual habitat.
I had seen some demonstrations down at KSC a number of years ago that were very visually convincing of this type of technology and the ability to move it off a surface. It's not 100% efficient, as you've pointed out in your studies, but I personally, if we can develop that into the hardware and have it be part of the operational scenario where we just try to keep it off all the time, we're going to be in a better shape in the long run.
It's awfully pervasive. If you've seen astronauts, I had somebody suggest to me, well, we'll have the astronauts move around slower so they don't fall down. That's it. That doesn't work, guys. They're going to fall, and they're going to be immersed in it, covered with the stuff.
Yep.
And places where they can't reach around. You can't reach unless your buddy does it for you.
I mean, I think the main thing is we are going to have to use multiple different techniques to clean off different things, right? I mean, my group and I, we've talked about making a handheld dust mitigation device that the astronauts could take with them to clean off, devices and tools and stuff outside of the habitat. But we've also talked about, we're going to need an airlock with some sort of dust mitigation system inside of it. I've also talked to other folks that are working on developing like films and materials that the dust just doesn't stick to in the first place. And that would be something they could apply to like camera lenses or, thermal panels, things like that, so that we don't even have to worry about mitigating it. So I think we're just gonna have to do a bunch of different things because, a handheld device doesn't work for everything, an airlock doesn't work for everything, a film doesn't work for everything, but the point is to keep the dust from coming into the habitat at all.
Yeah, that's a good point. You wouldn't want to have anything woven necessarily if you're trying to do that. Maybe.
Right, and one thing to consider is also the cost. That's why my group is actually pretty interested in having an external electron beam source that we can use to clean things off rather than an integrated electrostatic system, because that just makes the cost of production skyrocket.
Yeah. In addition to the pulmonary effects, as everyone knows, the finest fraction of lunar material is highly abrasive, and it's very abrasive to suit surfaces, anything that articulates or moves. It can jam it up. We did do a handful of studies that looked at skin abrasion and at ocular effects when that is in the eye, if you get it in your eye. And there's different things that we need to be considering on how we're going to be washing the eyes out when you get it in your face by accident. We also need to be considering what kind of garments we may want to have against our body, because as we learned from some of our abrasion studies, the type of garment that was worn either increased or reduced the abrasive nature of the dust that we introduced in the study. It turns out cotton actually seems to create a better boundary to reduce abrasion against astronauts or against a simulated skin. But again, this is just one example of a number of possible ways to mitigate these effects. Well, Doug?
Yeah, I would say that we have some also chats here. Ian Wells was saying about some development about liquid nitrogen to remove dust. So Ian, if you want to include that in the conversation here, feel free to unmute yourself and also share.
Yeah, I sent the poster in the chat. I didn't know about this conference until a few weeks ago. So I presented that poster at the Cryogenic Engineering Conference, but we've had very good removal just in kind of ambient conditions with liquid nitrogen. It uses the Leidenfrost effect and a few other effects that we're still figuring out. But we've had very good removal, and we're planning on doing testing in a vacuum chamber very soon. It doesn't mitigate the very, very small particles that you all have been talking about. But for everything pretty much over 3 microns, we are confident that it's able to mitigate them.
Have you told the folks at Johnson that you're considering blowing a nitrogen gas by their suits?
We did get funded by the Big Idea Challenge. I'm not sure. I don't remember which center that's through.
Suits are a spacecraft, and we had to be very, very careful we didn't tear them or damage them in any way.
One of the things that we're definitely looking into is how the treatment affects the spacesuit material. So far, we don't have any, we haven't visibly seen any degradation of the suit material, but we haven't extensively looked at it yet.
I just had a vision of the astronauts being required to put a mask on with a filtration system for all the time that they're inside the habitat after they've been out on the moon. That's another idea.
I like it.
So I guess sort of a general question, what would take priority between now and the Artemis mission? Would it be understanding the toxic and chemical pathways of lunar dust toxicity, or trying to mitigate the dust?
Well, I think that's a great question, Donald. It seems like keeping it out might be an easier problem, at least at first glance, but although technologically that might be very challenging. If we're thinking about using medical interventions to reduce the biological effects, I think that might be further off. And I don't know what that would be. So unless there's some kind of chelating agent or iron scavenger or the like, as you pointed out, some of these particles that are extremely small can cross the blood-brain barrier. And that's a whole area of much needed study too. And I would predict, and I'm not familiar with that literature, but there may be a body of literature that's out there that sort of discusses a lot of that as it relates to other kinds of fine-grained dusts.
Okay. I mean, if like understanding the toxic pathways is important, then then having like an in situ sort of like rover on the lunar surface would probably be the best option, and trying to find ways to sort of send like these cells to be exposed to this dust and sort of see what very, very fresh lunar regolith has on the effect on living tissues or living cells, compared to trying to spend so much time and effort trying to replicate lunar dust here on Earth.
Yep. In my opinion, the most interesting questions that need to be addressed is the interaction of planetary dusts with life from Earth. And because we can't avoid it, it's going to happen. And if we can develop some small Pathfinder-like experiments that will expose, as you pointed out, model organisms to dust in the lunar environment, it's going to help us better understand both short and acute and potentially chronic effects of short and long duration missions. And the same thing holds true for, we're talking about the moon, but on Mars, in parts per million exists perchlorates that are known toxic, chemically reactive hyperchlorates. So if we can start doing this kind of work on the moon, it's going to help us prepare for future exploration elsewhere. And I think it's something we really need to do. And perhaps we can take a step through a PRISM call to begin to explore this and maybe follow on missions.
Yeah, definitely.
I agree. It's just I think we better get some masks ready for these first few crews.
Yeah, I think that's the best option, honestly. If we can find ways to mitigate, that's going to be the best option. Just give them a mask, and maybe by the next mission we'll have it better figured out.
Yep. And what would be really interesting would be to sample, what is captured by the masks and what is not captured. If there's a way to build in that kind of control. And that this will then tell us more about the occupational exposure these individuals in the lunar environment are actually, experiencing. So I really like this idea of wearing masks. It's a great idea.
Now, this might be a little bit broader than just the lunar dust, because there's a lot of talk about doing in situ 3D manufacturing. And in the 3D manufacturing process, even though there's good containment, there's always small particles that escape. And so just in the manufacturing process, you may be generating toxic particles that also you should be protecting against.
Exactly. Yeah, I think that's one of the big take homes here is what's the way we can routinely sample the atmosphere of a habitat for any airborne particulates, and the use of masks potentially as a mitigation strategy when in the habitat. What are some others? These are great ideas.
I mean, like, it's probably more unrealistic. I've heard other people bring this up, like a shower, but I mean, you have to get all the water up there first.
Yeah, that's right.
Yep. Don, you said something about heating increases radical production. Is that, I was typing a response in the chat at that point and I missed that. Was it heat was increasing?
No, it was, so the metallic iron, we pretty much formed it on the surface by running the stream of hydrogen gas and then heating the sample up so the iron can more easily reduce.
Okay.
Yeah, it wasn't, I mean, I've read other papers where, you can raise the temperature up to a certain point, you do get more OH radical. So it's just possible that in human body temperature you get a bit more. But no, the heating in my talk was just trying to reduce the samples or getting iron on the surface.
Okay. Well, I think we're well over the discussion period limit here.
Yes.
But this is really interesting that as many folks have hung in on this discussion period. And clearly it's pointing to the fact, in my opinion, that this is a really important topic and that the evidence and data that has been presented, lends itself to an important area of current and future research needs for both, current and future missions on the moon. And so I would invite any and all of you to stay in contact with myself and Doug and all the other panelists to figure out ways that we can potentially work together to begin to address some of these really important topics.
Yeah, absolutely. I agree completely with you. And I think we had the opportunity to reflect about the importance of not only mitigate dust, but trying to work around of some aspects to reduce toxicity and the damage that can cause on humans. Yeah. Thank you all. Yeah.
And this is Mike, just a quick reminder, there is a networking session after this. So if you want to continue your discussions in GatherTown, everyone's going to be in the conference room section. So it's a great place to keep in touch. See you there.
Thanks, everybody. Much appreciated. Feel free to reach out. I look forward to hearing from each of you.
Thank you. Bye.
Recording stopped.